Hello, I'm Dr. Ken Beagleisen. In 1972, I proposed to my teachers at Cornell University that DNA was non-helical inside cells. I didn't think there was anything particularly controversial about it, yet I immediately found myself up against a solid wall of resistance. I didn't understand the resistance then, and I don't now. I thought that the age of prejudice and intolerance for new ideas went out with the Galileo Inquisition 400 years ago, but apparently that's not the case. 20 thankless years later, another scientist, Professor Tai-Te Wu, whose work we'll be discussing shortly, provided the first well-controlled study which directly addressed the question of helicity, or lack thereof, in DNA in living systems. The result of the Wu experiment was that DNA proved to not be helical in E. coli plasmids. You might think that this experiment would attract some attention, but to this day it is almost totally ignored. Well, another decade has now passed. This year I was fortunate to have been able to publish my most significant contribution to this very difficult field, namely the solution to a 50-year-old mystery: the structure of the protamine DNA complex. Since protamine is the very simplest of the nuclear proteins, being little more than a long string of arginine residues, its structure, in principle, should have been solved 50 years ago. And it would have been had scientists been open-eyed and open-minded enough to consider the possibility that DNA, in real life, might not have the helical twist found in synthetic laboratory crystals. The subject of protamine structure is covered in Part 2 of this presentation, entitled The Probable Structure of the Protamine DNA Complex. In the current presentation, however, we're going to look at the history and science of the arguments both for and against helicity in native DNA. To get started, let's look at the history of the problem. This is the world-famous Watson-Crick structure. As much or more so than any discovery ever made, it has changed the course of human history, opening the doors to the entire world of molecular genetics. Its structural features are, in general, proven way beyond any shadow of a doubt, but startlingly, one aspect of the structure, namely the helical twist, not only remains unproven, but in fact is contrary to all reason, and also is controverted by the weight of physical evidence. Before proceeding, a word is in order about the rotating virtual models you will be seeing throughout this presentation. First of all, I must thank Mercury Computer Systems for making their Amiramole program available for these studies, since these movies are all Amiramole exports. Secondly, I must point out that in general, and I think perhaps invariably, the direction of rotation in each Amiramole export is to the right, i.e., the direction defined by the right-handed rule of electromagnetism. You may think, however, that in some instances the molecule seems very definitely to be rotating to the left, or even changing directions every so often. This is an illusion which comes about because there's no perspective in these models, and the size of the atoms and bonds does not decrease when they move into the background. The situation is quite analogous to the old perspective problem with a two-dimensional representation of a cube. I'm sure you've all seen this picture before. If you stare at it long enough, the letter A will seem to move back and forth from the front of the picture to the back. There is no correct interpretation. It all depends on your perspective. Now take a look at the Watson-Crick structure again. If it seems to be rotating to the right, then all is well. If not, don't drive yourself crazy trying to force your eyes to see differently, because in most cases the point being made is not affected by the perceived direction of motion. The history of the Watson-Crick structure was picture perfect for about 10 years. Then, in 1963, a monkey wrench was thrown in. Here's a photo many of you may remember. It changed the history of molecular biology forever. It's Australian researcher John Cairns' world-famous autoradiograph of the E. coli chromosome, revealing the structure of that chromosome to be a closed circle. In this instance, we've caught the circle in the act of replicating, which will give rise to two daughter chromosomes, both circular. It is now known that all bacterial chromosomes, all plasmid chromosomes, and most virus chromosomes are also circular. The viruses whose capsids contain chromosomes which are not double-stranded circles have an intracellular replicative form which is, so the circular structure appears to be ubiquitous in nature. Why is this a problem? Here's a picture from my Non-Helix website. The caption reads, "The strands of a Watson-Crick double helix are locked together. If you cannot appreciate this from the drawing, make a model from string." I'm going to save you the trouble of doing that. The problem, which is minimized by the helicists, is actually one of enormous magnitude, and I'm therefore going to illustrate it extensively so that you realize that the Watson-Crick structure, pretty though it may look, is not a good choice for DNA in actual living, replicating systems. The linkage between circular DNA strands which are locked together by a helical twist is like the linkage between the links of a chain. Here's how you make a chain. First you start with a closed metal loop. Then you pass another length of metal through the loop. Then you seal it. If this chain was actually made of metal, you'd need a strong bolt cutter to get the links apart. The situation with DNA is far worse, with each strand mutually wrapped around the other not merely once, like a metal chain, but thousands and thousands of times, in some cases perhaps even millions of times. Here's a rope model of a circular chromosome with a Watson-Crick structure. When you try to separate the strands, you just get a terrible knot. Without a doubt, the strands of a circular chromosome with a helical twist are extensively linked together, a very awkward situation for a molecule whose main purpose in life is replication. When I first realized these things, in my senior year at Cornell in 1972, I immediately concluded that DNA probably didn't have a helical twist inside cells. As the caption says, wouldn't this make more sense? That is, wouldn't logic dictate that the single most probable solution to the problem would be a non-helical structure, whereby the strands could separate relatively effortlessly during cell replication? Here are two schematic representations of what non-helical DNA might look like. In A, you have large regions of right-handed helicity alternating with equal lengths of left-handed helicity. This is obviously not a structure very likely to be found in nature. B shows a more likely alternative, where the chromosome alternately twists a bit to the right, then to the left, repeatedly throughout its length. A number of proposals based upon this concept have been put forth, as we shall see. These and other models not shown yet all have one thing in common. The strands of DNA in these models are topologically non-linked and will separate readily when the chromosome replicates. I refer to all such models, regardless of their molecular specifics, as TN models. Although by 1963 it was well established, to the satisfaction of nearly all, that DNA was a right-handed helix when stripped of all proteins, dried, and crystallized, this hardly proved that it would have the same structure in the cell nucleus. The nucleus, after all, contains not only DNA, but also an approximately equal weight of highly positively charged basic protein, which would surely exert some sort of effect on the conformation of the DNA. What did Cairns think? We now come to what I'm calling a turning point in history, and I mean that quite literally, because I believe that the words of this article steered an entire generation of molecular biologists down the wrong path. The setting was the Cold Spring Harbor Laboratory in Long Island, without a doubt the mecca of molecular biology. A little under a year after the publication of his landmark autoradiographs of E. coli, Cairns had been invited to participate in a symposium on DNA structure and replication. He had had nearly a year to think about it. In order to understand what happened there on that day, you must keep your historical perspective. First of all, the fact that the strands of circular DNA resist separation when denatured was not yet known. None of the enzymes currently believed to be necessary for the unwinding and rewinding of circular DNA during replication had yet been discovered. All that was known was that chromosomes were circular, presumably with a massive degree of topological linkage, and that they were yet able to separate during replication. Howard Cairns, the world's ranking authority, explained this. In my opinion, for what it's worth, the best explanation was that the E. coli chromosome simply did not have the literal Watson-Crick structure, and that the strands were in fact topologically non-linked. The only obvious alternative was that all the twists were painstakingly unwound in each generation and rewound in the daughter cells. Surely an awkward proposal. Well, here's what he thought. Let us read. To make the diagram in a sense complete, some provision must be made for free rotation of the unduplicated part of the circle with respect to the rest, so that the parental double helix can unwind as it is duplicated. This provision, which we may non-committally refer to as a swivel, has been placed at the junction of starting and finishing point. Hey, there's no mention at all, either here or anywhere else in this entire Cold Spring Harbor Symposium volume, of the possibility that maybe the strands simply aren't twisted together, and therefore don't need to be unwound. How did Cairns rule that out? Who told him that DNA had to have a helical twist? Did he even think the problem through? Those of you who are familiar with the theory of discontinuous DNA replication must keep in mind that it was not known back then. What, in terms of the level of knowledge which existed in 1963, can we say about the implications of the swivel theory? In particular, if all of the E. coli purported Watson-Crick twists need to be removed, how fast is the chromosome spinning? In order to answer this, we need some basic statistics about E. coli, and here they are. The cell is about 2 microns long, but the single circular chromosome is 1.35 millimeters long. Why, that's 700 times as long as the entire cell. That means the DNA is really packed in tight. Here's the crux of the matter. There are 4 million base pairs in E. coli. Armed with this information, we can now answer our question. How fast is the E. coli chromosome spinning? In log phase, E. coli replicates in 20 minutes. Under optimal conditions, the daughter cells begin to divide before the parent cells have fully separated. If the E. coli chromosome has the Watson-Crick double helical structure, then with 4 million base pairs, there would have to be 400,000 Watson-Crick twists. Every one of these twists would have to be unwound and rewound in the space of 20 minutes. The conclusion is that the chromosome in log phase must be spinning at 400,000 divided by 20, or 20,000 RPM.
This is my Black & Decker power drill. Look what it does to this piece of wood. How fast do you think this thing is going? The manual says 1,000 RPM.
So the concept Cairns sold the molecular biological world in 1963 was that the chromosome of E. coli was spinning 20 times faster than an electric drill, i.e. the speed of an ultracentrifuge. Do you really believe that this chromosome, or even part of this chromosome, is spinning at 20,000 RPM? It seems unlikely, does it not? Are all the processes of life, including transcription, recombination, and DNA repair, taking place as the chromosome spins at 20,000 RPM? Not very likely. If we attempt to evaluate Cairns' view of circular DNA replication by examining his published writings from 1963 to 64, we are compelled to conclude that he did not think the problem through. How did he reach the conclusion that DNA replicated by virtue of a swivel? No such structure was known at the time. Why did he make no mention of the severe rotational problem involved in replicating a circular Watson-Crick structure? And, most of all, why did he not even mention in passing the seemingly obvious possibility that DNA might not be helical in cells? Although it didn't take long to realize that entire chromosomes don't spin at 20,000 RPM, there's never been any doubt that small molecules can and do spin that fast and even faster. Therefore, the concept quietly arose that DNA replication was discontinuous. If so, then only a part of the chromosome would have to be spinning at 20,000 RPM at any given moment, as depicted in the following somewhat crude movie. It's true that our knowledge of DNA replication has advanced astonishingly, and that the enzymes topoisomerase and gyrase theoretically allow unwinding of DNA as the DNA replication fork advances along the chromosome. But if you look at this lovely drawing from Germany, you'll note that the incredibly complex and minutely coordinated activities of the various replicative enzymes take place within a flattened out, that is, non-helical region of activity in the replicating fork, with the topoisomerase placed at the entrance like some sort of guard. The roles of the enzymes within the fork are apparently well characterized and complicated in the extreme. Leninger refers to these events as elegant enzymatic choreography, and that description is, if anything, an understatement. What we're dealing with here is a miraculous sequence of closely linked processes which proceed with blinding speed and unfathomable accuracy. However, the supposed winding and unwinding events at the ends of the replicating fork are a much more murky affair. There is no demonstrated temporal relationship between the well-documented choreography of the enzymes within the replicating fork and the murky activities of the topoisomerases and gyrases without. The presumption that DNA must be unwound and rewound during replication remains in the realm of theory, known as the two-domain hypothesis. This hypothesis is based upon the fixed, immovable belief that DNA has the Watson-Crick structure. If so, then it is necessary to accept and believe that the DNA in front of a replicating fork, represented here by an orange arrow, will become overwound as the fork moves, and that likewise the DNA behind the fork will be stretched out, becoming underwound. These abnormal windings, it is said, must be removed by topoisomerase and gyrase respectively. But is this true? Most of the topoisomerase and gyrase research is based upon in vitro studies, where the native structure of DNA is destroyed. As soon as you remove DNA from its natural protein environment, it's going to wind itself up into a helix, and everything you discover subsequently is at risk of being laboratory artifact. Even if these enzymes do what they are claimed to do in vitro, isn't it possible that in the living cell, where the DNA structure may be non-helical, that their true roles may be in other processes, such as DNA repair? There's no way to know by direct evidence. It would be consistent with my admittedly argumentative nature to try to find fault in the two-domain theory, but the literature on the subject is so confusing, and the publications so mutually inconsistent, that it's hard to find a well enough established fact to merit a critical analysis. The typical two-domain experiment involves either enzyme mutants or administration of enzyme poisons, neither of which necessarily even stops DNA replication, but may merely slow it down. The products generated may or may not be supercoiled in various senses, according to two-dimensional electrophoresis gels, which are exceedingly difficult to interpret. Virtually any result reported in one lab has been contradicted by a different result elsewhere. In the presence of such uncertainty, it would be foolish to draw too many conclusions from this line of research. Besides, none of those enzymes were known in 1963. Therefore, we still have no explanation for the curious fact that Cairns insisted that DNA replication had to be by means of a swivel. I can think of 3 explanations. Number 1, perhaps Cairns wasn't intelligent enough to figure out that DNA was not necessarily helical in cells. This, of course, being a very unlikely explanation. Perhaps experimental evidence existed which proved, or strongly suggested, that DNA was indeed helical, not only in synthetic laboratory crystals, but in the nuclei of living cells as well. Such evidence was, in fact, starting to emerge, but there's no evidence that Cairns, or any other speaker at Cold Spring Harbor at that time, knew about it. They certainly made no mention of it. Or perhaps it had already become politically incorrect, as early as 1963, to speak publicly of any DNA structure other than the double helix, because DNA had already risen to the level of a quasi-religious icon in the minds of most scientists. And the correct answer is number 3. It had already become politically incorrect, even as early as 1963, to speak publicly of any DNA structure other than the double helix, because DNA had already risen to the level of a quasi-religious icon in the minds of most scientists. You can say that this picture is a gratuitous insult or a cheap shot, but it is neither. It is a high-order and well-intentioned satire to dramatize a serious problem which arose in 1963 and persists almost full force to this very day. Whether you're talking about viral, bacterial, or human chromosomes, or the structure of DNA in the nucleosome, or the structure of DNA when complexed to the lac repressor, or any other modulator of DNA activity, you find, with not a single exception I know of, that the concepts listed at the top of this slide are required, as if by statute. DNA is a helix. No other structure is possible, and no other structure can even be discussed. So we're going to have to do something about that. A logical question arises. Why on earth should DNA, in the presence of the strongly charged basic proteins of the cell nucleus, have the same structure as DNA in the laboratory, where all those charged proteins have been artifactually removed? Is there any reason to even expect that? Now, at the risk of being accused of saturation advertising, I'm going to belabor this issue a lot. Those of you who are practicing nucleic acid protein chemists will surely deny believing this, but you're just fooling yourselves and you know better. Without a doubt, the presumption that DNA has the same structure, whether or not nuclear proteins are present, is so ubiquitous that it might almost be described as universal. So I am going to belabor this issue until a point gets across. Let's start with a rose bush. Is the structure of a rose bush with a trellis the same as the structure of a rose bush without a trellis? I think not. How about a man with a cane? Is the structure of a man with a cane the same as the structure of a man without a cane? Well, certainly not in this case. Now, those of you who insist that DNA must have the same structure, whether or not nuclear proteins are present, might also think that a bow and arrow has the same structure, whether or not the attractive young woman is present. In this case, we can do a little experiment. You can stand in front of the bow and arrow, and then we can remove the woman. Oops, that could be a problem. Well, no harm done. This time. You could say that all this has nothing to do with chemistry, but what if I told you that some influential group of senior scientists had promulgated a decree which stated that all enzymes must have the same structure, whether or not substrate is present? You'd laugh in my face, wouldn't you? If that was the case, after all, then half of all biochemistry would be null and void. Of course it's ridiculous. But then, why do you insist that, alone among all the chemicals in creation, one only, namely DNA, must have the double helix structure in every setting in which it's found? Okay, I admit, I've been doing my very best to present belief in the double helix in the most ridiculous light I could conjure up. That's because the notion should have been questioned by biochemistry's elite in 1963, and it wasn't. But, to be fair and even-handed, I must now admit that the story is more complicated than that. Biochemists unwilling to consider non-helical structures got a reprieve in the early 1960s, because at about the same time that Cairns was doing autoradiographs, a discovery by Jerome Vinograd and his associates demonstrated something that seemed to prove that blind faith in the Watson-Crick helix was justified after all. That discovery was that the chromosomes of some viruses were, like the chromosome of E. coli, closed circular duplexes. Additionally, however, they were small. whereas it remains true to the present day that because of its large size, it's almost impossible to manipulate a bacterial chromosome without breaking it into a shower of fragments. The small circular chromosomes of viruses are quite stable to ordinary manipulation. They can be shaken, stirred, frozen, and thawed without breaking, so they are very amenable to various physical studies. Among the first of these studies were denaturation studies. These, to no one's surprise, showed that the strands of circular DNA do not separate when boiled, and the strands of circular DNA do not separate at alkaline pH. In the latter instance, it was demonstrated through studies such as the measurement of light absorption at 260 nanometers that at high pH there was a complete breakdown of the base paired structure. Yet all attempts to separate the strands physically failed, and it became very clear that they were somehow linked together, even when denatured. This was considered to constitute totally satisfactory evidence that small viral DNA had the Watson-Crick structure, where, as we have seen, the strands would be locked together, and no separation would be expected even upon denaturation. Thus, the unwillingness of molecular biologists to consider non-helical structures for circular DNA seemed to have Mother Nature's seal of approval. But shouldn't someone at least have asked the following question? Is it possible that there's something about circularity which imparts unexpected characteristics on DNA, so that under conditions where the strands would separate if linear, they do not separate when circular? The answer is emphatically yes. Circular DNA turns out to have properties entirely different from those of its linear cousins. The first studies in this area were done by Jerome Vinograd and René Delbecco, both of whom were major figures in American science. Working with the chromosome of polyoma, a small mammalian oncogenic virus, they found what at first seemed to be a very peculiar behavior of the DNA as the pH was increased. At first, as the pH approached 12, the DNA clearly and significantly decreased in density. Thereafter, it increased relentlessly until pH 13, at which point it leveled off and became constant at higher pHs. A painfully detailed study of these phenomena was carried out by Robert Warner, a colleague of Vinograd's. Most of the work was actually done by Mark Rush, a postdoc in Vinograd's lab at Caltech, and Bill Strider, a doctoral student at NYU School of Medicine. I knew them both very well. Mark joined the faculty at NYU, where he was my thesis advisor, and Bill Strider was a postdoc in the same department for most of the 5 years I spent there. Shown here is a preliminary view of Rush's data, utilizing not polyoma, but the replicative form, or RF, of the chromosome of Phi-X174, a virus about the same size as polyoma. You're going to have to pay strict attention to this data if you wish to understand circular DNA, because the entire argument, which has been swallowed whole by the molecular biological establishment with respect to the necessity of believing in the Watson-Crick structure, is based upon this work. If you don't take the trouble to understand this alkali denaturation data, as I walk you through it, you will never understand the structure or topology of circular DNA. We shall have need to understand everything in this slide, but for now I'd like to draw your attention to the lower curve, that is, the white circles, which show the sedimentation coefficient of the Phi-X174 chromosome. The sedimentation coefficient, S, is the rate at which it drops in a cesium chloride density gradient ultracentrifugation study. If you're not familiar with the procedure, which was one of the backbones of mid-20th century biochemistry, just think of S as being a measure of density, although in this case, it's not only the primary chemical structure which determines density, but also the secondary and tertiary conformational changes which take place as the pH changes. The drawings above the graphs illustrate the sorts of tertiary structures which give rise to the changes in S. You'll note that in one of the drawings, DNA is depicted as an open circle, or oval to be exact. If you look closely, you'll see that I've neglected to indicate any Watson-Crick helical twisting, because the nature and direction of helical twisting is the very issue which forms the substance of this slide presentation, and I'm making no presumptions about it, yet. The other three drawings depict the DNA as having a higher order twisting, known as supertwisting. It's primarily the state of supertwisting that determines the density and hence the S value. The situation is entirely analogous to skydiving. If the skydiver has his limbs spread out, he drops relatively slowly, with a terminal velocity of only 90 miles an hour. But if he goes into dive position, he minimizes air drag and his terminal velocity more than doubles to 190 miles an hour. The DNA sketches below show the analogy. When DNA appears as an open circle, it has a relatively low sedimentation coefficient in cesium chloride velocity gradient ultracentrifugation, and a relatively slow rate of migration in an electrophoretic field. But when it's supertwisted, friction is reduced, and it will move more rapidly during either centrifugation or electrophoresis. Back to our graph. Note that at a pH of about 11.8, S drops to a minimum. Then it increases to a maximum at a pH of about 13. If the DNA is neutralized in stages, we get the upper curve, i.e. the black circles. Note that S never returns fully to its pre-titration value, but remains permanently elevated. How can we explain this? The so-called standard explanation, concisely illustrated by the drawings which appear in the graph, starts with yet another unfounded assumption, namely that DNA is, for some strange reason, synthesized underwound, which causes it to have superhelical twists at physiological pH. If you're not familiar with the topology of circular DNA, don't worry. That's what this slideshow is going to be all about. For now, just accept that circular DNA, as usually isolated in nature, is in fact found to be superhelical, in addition to whatever secondary helical winding it does or does not have. Here's the picture again without the skydivers this time. On the left side of this slide, we see a drawing of a DNA classic Watson-Crick double helix, which has been circularized. This open circular form is not the form in which most naturally occurring circular DNA is isolated, however. In general, circular DNA in nature is superhelical, as illustrated on the right. When the circular helical duplex is further twisted to impart a higher order twist, it is generally referred to as a tertiary twist. The Watson-Crick helical twist, on the other hand, is referred to as a secondary twist. Note the directions of helical twisting, which are correctly depicted here. The Watson-Crick structure on the left of the picture has a right-handed twist. This means that as you follow it up, you find yourself moving to the right. This is true regardless of which way the drawing faces. If you turn it upside down, it remains right-handed. The direction of winding of the superhelical turns on the right side of the picture is also right-handed. This too is correctly depicted, since this is the direction of superhelical twisting ordinarily found in nature. DNA topologists generally refer to this not as right-handed, but rather as negative supertwisting, for reasons I'll explain shortly. For now, however, I'm going to assume that most viewers of this slide presentation are not DNA topologists, and it's far less confusing, with respect to the concepts we shall discuss, to use right-left terminology for both secondary and tertiary twists for the time being. Let us now turn to the basic rules of DNA topology. I'm going to state them succinctly first, then illustrate them. So if they don't seem clear at first, hang on, because the concepts are not really all that difficult. The first rule is this: the number of secondary helical turns in fully intact circular DNA, when it is constrained to lie flat, that is in a plane, is absolutely fixed at the time the rings are closed. In our so-called heretical non-helical model to be presented shortly, that number is 0. In the classic Watson-Crick crystal structure for linear DNA, the number is 1 complete right-handed helical turn per 34 angstroms of length. In circular DNA as isolated in nature, if you believe in the Watson-Crick structure, then that number actually turns out to be 5 to 7% fewer turns than found in corresponding linear DNA, as we shall explain shortly. Whatever the number is, it cannot be changed, unless one of the strands is broken open. In spite of the fact that I'm about to propose a non-helical structure for DNA in living systems, I nevertheless present the following second rule of DNA topology. Under physiological conditions of pH, temperature, and ionic strength, the only known fully relaxed unstrained structure for DNA of average base composition is the Watson-Crick structure, with one full secondary helical turn per 34 angstroms of length. A circular duplex chromosome which, at the moment of covalent closure, has either a greater or lesser number of secondary helical turns per unit length will be under strain. The situation is really quite analogous to an ordinary metal spring. If I was to stretch this spring, altering its pitch, then when I let go it would immediately snap back to its normal length. The same if I compress it. Like this spring, DNA wants, so to speak, to have a certain pitch, which in the absence of complicating factors is 34 angstroms per helical turn. If you either overwind or underwind the DNA, it gets upset, just like a metal spring does. Now here's the third principle of DNA topology. Tertiary, i.e. superhelical twists, increase the tightness of the secondary winding of a helix whose twist is in the same direction, and decrease the tightness of the winding of a helix whose twist is in the opposite direction. If you don't understand what I mean, relax, because I'm going to show you some models. This is the sort of thing which is very easy to see and grasp, but very difficult to explain in words. Let's look at some pictures. The left side of this slide shows a Watson-Crick circular double helix with exactly and precisely 2 right-handed twists. Note that each strand crosses the other exactly 2 times. In real DNA, these crossings are very intimate and occur within the constraints of the exact dimensions of the double helix. They cannot be removed without affecting the geometry of the entire helical structure. Now, what if the chromosome didn't like the way it was twisted? That is, suppose there were too many or too few helical turns, or even left-handed turns. What could the chromosome do to cure the defect? Look again at the picture. The cure is to take on superhelical turns in the opposite sense. Look at the right side of the picture. This is the structure which results from the introduction of 2 left-handed superhelical twists into the chromosome. Please look at the structures on both sides of the drawing and verify that the directions of helical and superhelical winding are opposite, namely right-handed in the original chromosome and left-handed in the superhelical structure. Note also that in the superhelical structure, neither strand ever crosses the other. The introduction of 2 left-handed superhelical twists has totally unwound the secondary helical twists in the original structure, replacing them with a new structure which has only superhelical crossings. Now, you may be wondering what benefit there is in removing secondary twists if we're just going to add tertiary superhelical twists. That's a good question. In order to see the benefit, let's look at a real model made from rope. This is the rope model which was the basis of the drawing above. This model is the ultimate in simplicity, having only one single right-handed Watson-Crick twist, whose secondary crossover is indicated by the arrow. When a single left-handed superhelical twist is added, in the direction indicated, the single secondary strand crossover is eliminated, just as we saw in our previous 2-twist drawing. If we follow this structure around, we see that once again the strands never cross in the secondary structure, but they cross in the tertiary sense. Now let's see what the benefit is to the DNA. And here it is. If we look in 3 dimensions, we see that the strands, which seem to be quite intimately close as they cross superhelically in the flat picture, may actually be quite far apart. Note that there's room to put a ruler between the strands so that the superhelical crossing actually has no steric effect on the structure of the chromosome. Bearing in mind what I said about the chromosome not being happy when either under or overwound, we can now see the secret of reducing helical strain by the winding in or out of superhelical twists in the opposite sense, namely that a small number of superhelical twists in the opposite sense do in fact have the ability to significantly reduce secondary helical strain and add no additional element of steric hindrance to the molecule. The process of removing secondary helical strain due to over or underwinding through the formation of superhelical twists in the opposite sense cannot, however, continue indefinitely. There does come a point where an excessive number of superhelical twists will cause the DNA strands to be brought so close together that the negatively charged phosphate groups will begin to repel each other, discouraging further superhelical twisting. This is illustrated in the following drawing. This drawing, like some of the previous drawings, makes no attempt to indicate the direction of secondary helical twisting, but illustrates only tertiary superhelical twisting. It attempts to make the point that the addition of a small number of superhelical turns, as in picture B, to an open circular duplex, picture A, does not force the strands on the opposite sides of the duplex to lie too close together, but continuing to add more superhelical turns will eventually do so, as shown in C. There will therefore be an equilibrium number of superhelical turns which will come about as a result of a balance between the benefit of removing, or adding, superhelical twists to neutralize unwanted secondary twists, and the drawback of adding steric strain due to DNA backbone phosphates being forced too close together. To summarize, we now show DNA in 3 stages of winding: normal on the left, underwound in the middle, and overwound on the right. In each instance, I've inserted a scale calibrated in units of 34 angstroms of length. That is, each numbered unit on the y-axis corresponds to a distance of 34 angstroms, the length of a single turn of Watson-Crick DNA under normal conditions. Thus, on the left, the 10 units of length correspond to exactly 10 turns of DNA. If this DNA was circularized, it would be in a relaxed open circular conformation, as depicted in the drawing below. In the middle, however, the DNA has been partly unwound, that is, it has become underwound, so that there are less than 10 turns of DNA along the same 10-unit length, in this instance the number being between 9 and 10. This DNA is under strain, and, if circularized, it will attempt to return to its normal winding. In order to accomplish this, it takes on some right-handed superhelical turns, as depicted in the drawing below. Conversely, on the right, the DNA has somehow become overwound, and now has more than 10 helical turns per 10 units length. It wants to unwind, and in order to do so, it takes on some left-handed superhelical turns, as in the drawing below. Hopefully these drawings and photographs make these principles clear. We're now ready to examine and understand the alkali denaturation curve of Phi-X174 DNA. The data are taken mainly from the publication on the subject by Rush and Warner. We'll start with a traditional helicist explanation for these data. At physiological pHs, the chromosome has a middling sedimentation rate of about 21s, significantly higher than that of a relaxed chromosome because, we are told, Phi-X174 DNA is underwound at the time of its creation, and therefore takes on right-handed tertiary supertwists to increase the right-handedness of the secondary helical winding, as depicted in the oversimplified drawing above the curve. The proposed underwinding in traditional theory is 5 to 7%, which, in a chromosome the size of Phi-X174, if it's presumed to have the Watson-Crick structure, would amount to about 550 secondary right-handed Watson-Crick helical twists and about 25 to 30 right-handed superhelical twists. I've always found it odd that people are so ready to believe that chromosomes are routinely underwound. Exactly why should we believe this? There's really no logical reason for it. It's merely another assumption the helicists must make in order to force the data to accommodate to the Watson-Crick helical structure. The closest thing to a rational explanation offered by the helicists is that the 25 to 30 supertwists somehow facilitate packing of the DNA in the virion, a rather arbitrary proposal, one which hardly scratches the surface of the almost incomprehensible problem of packing huge lengths of chromosomal DNA into the tiny spaces nature provides for them. I have a much better explanation, but we're not up to that yet. Back to our data, as the pH increases, the hydrogen bonds between the base pairs of duplex DNA are progressively weakened, and the DNA begins to unwind. In our traditional helicist explanation, this means that the superhelical turns, which were, after all, only there to compensate for the chromosome having been closed in the underwound state, will become progressively less necessary, since a denaturing, i.e. an unwinding duplex, is perfectly happy to be underwound, and no longer needs superhelical twists to compensate. At a pH of about 11.8, the superhelical twists have all been removed, and the chromosome appears as an open circle. Now, as the pH continues to increase, the chromosome would like to continue unwinding, but of course it can't, because it's a closed circle with the secondary windings locked in. So now it supertwists in the other direction, with each new left-handed supertwist removing one of the now unwanted right-handed Watson-Crick twists. Each additional supertwist increases the compactness and density of the chromosome, resulting in a relentless increase in its S value. At the highest pH, around 13, the chromosome has become very dense, as reflected in the high sedimentation coefficient of nearly 50S. This form of DNA has been dubbed Form 4. What is the structure of Form 4? No one knows. And as far as I can tell, no one cares. In the 30-plus years I've been studying this problem, I've yet to see a single paper on the subject. I asked Bill Strider for his opinion, Bill being the man who probably did more of the actual laboratory research on the denaturation and renaturation of small circular DNA than any other scientist living. Bill got an annoyed look on his face and said, "It's just a tangled mess." Here's an actual picture from an early publication on alkali denaturation of circular DNA, showing the author's conception of the structure of Form 4. To this date, this remains the level of sophistication regarding this structure. It leaves much to be desired, does it not? All the behaviors we have discussed so far pertain to intact circular duplex DNA. What happens if a nick is introduced into a closed circular chromosome? To complete our study of the alkali titration curve for Phi-X174, we need to add the data for nicked DNA. The behavior of this form is indicated by the triangular data points and the blue lines. At this juncture, I'd better introduce some terminology. Form 1 is the name traditionally applied to covalently closed circular duplex DNA, such as is found in most viruses and plasmids. As we've already begun to see, the covalent closure, which locks in an unchangeable number of secondary helical twists, imparts striking topological properties to the molecule. Form 2 is the form which appears if one of the two strands is nicked. Even a single break in the sugar phosphate backbone allows the strands to rotate around one another, so that any deficiency or excess of secondary helical turns is immediately relieved. Therefore, in general, Form 2 appears as a relaxed open circle. Form 2 behaves like linear DNA and has none of the striking topological properties we've seen for Form 1. Form 3 is the form which results from cleavage of both strands, which linearizes the molecule. The terminology Form 3 is rarely seen, since linear DNA is usually just called linear DNA. It's included here just for completeness. Form 4 is the extremely dense form, which results from alkali denaturation of Form 1. As we've already seen, its structure is totally unknown. Although the data for Form 2 yield, for the most part, a straight line, there are some peculiarities in it. For now, we'll merely note that at pHs above 12, Form 2 splits into two components. The upper line represents single-stranded circular DNA, and the lower line, single-stranded linear DNA. There are two additional things I'd like to draw your attention to at this time. The first is that the sedimentation coefficient of Form 2 between pHs 11.8 and 12 follows that of Form 1. If you're paying attention, you'll notice that there's only one triangular data point in that pH range, and you might be tempted to conclude that I'm taking inexcusable liberties in the way I drew that line. But that's not the case. Alkali denaturation titration curves for other viral DNAs have emerged from the laboratories of Jerome Vinograd and other researchers, and all of them show a confluence between the Form 1 and Form 2 curves in this pH range. It's no mistake, and it's no taking of liberties. It's real, and it needs to be explained. This phenomenon, however, is never discussed in papers on this subject. That's because it can't be explained by Watson-Crick helical theory. It just doesn't fit. But it can be readily explained in our non-helical theory, as I shall demonstrate shortly. The second thing I would like to point out is the shoulder on the Form 1 denaturation curve, labeled chi, or, more accurately, chi. This was eventually proven in painstakingly detailed papers by Warner and his associates to be the pH range within which Form 1 becomes reversibly denatured, with a breakdown of base pairing. A few tenths of a pH unit higher, at pH 13, the denaturation becomes irreversible, giving rise to the upper Form 4 curve, that is, the black circles at the top. Notice, by the way, that the upper Form 4 curve also has a shoulder in the same region. The vertical bar of gray shading encompasses a pH region within which it certainly seems that both Form 1 and Form 4 are undergoing conformational changes. Interesting, no? What do you suppose it means? Once again, these shoulders are never discussed in published papers on these data. We, however, shall be discussing them shortly. Let us now go through this alkali denaturation data, only this time without assuming that DNA has any net Watson-Crick twists. Can we explain the data with a topologically non-twisted model for DNA? I'll tell you the answer to that right now. We can explain it, and we can provide an explanation that is better than the one offered by the helicists. I refer to all models of non-helical duplex circular DNA as TN models, where TN stands for topologically non-linked, the state of the two strands. There are a surprisingly large number of models to choose from, so first we are going to have to find a convenient way to visualize a TN chromosome. Here are two such ways. A is a model in which half the chromosome is right-handed and half left-handed. Such a model can be made from two rubber bands by merely twisting them together. In addition to the benefits I've derived from working with an $80,000 molecular modeling software program, I've also learned a lot from the lowly rubber band. If you get two differently colored rubber bands which are large enough, you can do some experiments. Here are some experiments done with some really oversized rubber bands. Look please toward the left side of the slide. In the top panel, labeled A, our oversized rubber bands are twisted together. If you look closely at the resultant structure, you'll see that it is right-handed on top and left-handed on the bottom. Although my hands cover part of the structure, you can pretty much see that the number of right-handed twists on the top is the same as the number of left-handed twists on the bottom, which, in this picture, appears to be 5 each, plus whatever lies beneath my fingers. This is no coincidence. When you twist rubber bands together in this way, every twisting motion of your hands automatically and simultaneously produces exactly as many right-handed as left-handed twists, and every untwisting motion likewise removes an equal number of right-handed and left-handed twists. The rubber bands remain, of course, topologically non-linked throughout, and they only stay together because I'm holding them that way. If I was to simply drop them, which I can't show you without a movie, they would instantly unwind themselves and fall to the table as two separate rubber bands, which is, after all, what they are. If, however, instead of simply dropping them to the table, I release the tension in these rubber bands by slowly bringing my hands together, as shown in panel B, then something very interesting happens. Superhelices spontaneously form. Let's look more closely. The formation of these superhelical structures is in no way the result of the physical properties of the rubber from which the model is made. This phenomenon occurs whether one uses rubber bands, string, or sewing thread. The longer and thinner the material used, that is, the closer it is to the proportions of actual DNA, the more readily these superhelical structures form. I would conclude that the formation of superhelical structures from circular DNA under strain is, in part at least, and maybe in total, a purely mechanical process, one which I wouldn't pretend to understand, but which can be clearly visualized in these models. Another thing which can be visualized in these models is a macroscopic demonstration of my so-called third principle of DNA topology, which stated in part that tertiary, that is, superhelical turns, decrease the tightness of the winding of a helix whose twist is in the opposite direction. If you look at this photo, you'll see the rule in action. As the right-handed secondary helical turns on top of the structure unwind, they turn into left-handed tertiary superhelical turns, whereas the left-handed helical turns on the bottom unwind into right-handed superhelical turns. One final observation on these rubber band models is that, whereas the twisted rubber bands in panel A are unstable and will fall apart as soon as the experimenter lets go of them, the super-twisted structures in B are, for some reason, quite stable and do not unwind when one lets go. This is illustrated in panel C, which shows that the fully superhelical structures no longer need to be held by the experimenter. They are completely stable. The panels on the right side of the slide show that all these phenomena occur with smaller rubber bands in exactly the same way. I can't explain this, so I'll just post this picture for the benefit of those among you who know more about mechanical engineering than I do. Although the A model provides a convenient way to visualize and study the 50% right-handed, 50% left-handed topological nature of tNDNA, it's obviously not a very likely candidate for DNA structure in real life. B, however, is a much more realistic model, where short right-handed and left-handed segments regularly alternate, each segment being less than a single full twist in length. This sort of structure was first proposed by the New Zealander Gordon Rodley in 1976, and, in a turn of events reminiscent of Alexander Graham Bell getting to the patent office first by 10 minutes, only a month later the prominent Indian biochemist V. Sasasekaran published essentially the same structure. These publications caused a small uproar in the DNA community, which Crick responded to in a manner we shall consider shortly. Rodley called his structure the side-by-side model. Everyone who's ever taken an interest in DNA topology has heard of it, but not too many people have ever seen it. Well, here it is in 2 dimensions. Let's look around. Here it is in 3D. This model was made from Rodley's published coordinates. He never lived to see this sort of virtual modeling software we have these days, and I'm sure he would have gotten a big kick out of seeing this. Crick thought that the side-by-side model was uglier than his double helix, which I suppose is an aesthetic judgment call. What is true is that the model is entirely hypothetical, not based upon scientific observations, but constructed entirely by modifications of the Watson-Crick structure. Now here's another TN structure which most people do not know about. It's the work of my friend and colleague, Clive Del Monte, and it's called the paranemic model, to distinguish it from the plectonemic or coiled model of Watson and Crick. The paranemic structure strongly resembles the Rodley structure, although it arises from an entirely different concept. Here, the sugar-phosphate backbones are right-handed helices, but they never cross one another. The structure as a whole, therefore, has no full twists, undulating instead in a Rodley-like fashion, as I've endeavored to show in this drawing. Clive has a preliminary virtual model, but it's not ready for showing. You can see a photo of his physical model on my notahelix.com website. The paranemic model is in no way an arbitrary exercise in alternative DNA structure, but rather an attempt to create an asymmetric model of DNA which is consistent with the results of 1953 measurements of DNA dimensions, taken in molecular monolayers in Langmuir troughs by James and Mazia. Any one of these models would allow DNA to replicate without a swivel and without the need to posit a rotational speed of 20,000 RPM at the replicative site. I actually believe that DNA in vivo has a different structure entirely, namely the structure proposed by an ingenious fellow named Tai-Tai Wu. The Wu structure is taken up in part 2 of this series, entitled The Probable Structure of the Protamine DNA Complex. For the remainder of the present discussion, I shall not assume anything in particular about the structure of circular DNA, other than that the strands are topologically non-linked. Now we come to the crux of the matter. Let us assume, for the sake of argument, that circular duplex DNA has the TN structure. What can we predict about the topology of the chromosome, specifically with respect to tertiary superhelical winding? Would it be a relaxed circle, or would it be a superhelix? Or is it just impossible to make any prediction at all? What you're going to see is that the helicists, led by Francis Crick himself, automatically and mindlessly do make assumptions about this, and their assumption is that if TN DNA existed, it would be a relaxed circle. Is this reasonable? Have they thought the matter through? To put this in perspective, let's do a review. On the top is what has now become the so-called classical view, namely that DNA is a right-handed double helix. We know that when isolated in nature, circular DNA is, in fact, a superhelix. But is this what you'd expect for a circularized Watson-Crick chromosome? Of course not. There's no earthly reason to presuppose that merely circularizing a Watson-Crick length of DNA would give rise to anything other than an open circle. So you've got to add the additional arbitrary and irrational assumption that the DNA is underwound, as previously discussed. This is portrayed here by the thumbtacks, which indicate that circular DNA, as isolated in nature, will not lie in an open circular conformation unless restrained. What about TN DNA? Suppose that you found a way to close a length of DNA into a circle without any net helical twists. What would its structure be? Would it be an open circle, as portrayed on the left? Or would it be a superhelix, as portrayed on the right? You may think that this question requires years of experimentation and reams of data to answer, or, in the absence of such, a near Einsteinian intuition and intellect. Well, you don't need any of that. But you do need 3 things. 1, you need an IQ above 100. I'm sure everyone watching this presentation is at least as intelligent, and probably a lot more intelligent than me, so that shouldn't be a problem at all. 2, you need sufficient humility to admit that it's at least possible that there's something basic about DNA that you don't know. But most important of all is 3, you need to be sufficiently free of financial attachments to publicly traded biotech companies to maintain the capacity for independent thought, as dramatized by the following very scientific graph, which shows what happens when scientists get too rich and too successful. I've lived long enough to see science go from something resembling a temple of truth, albeit with many flaws, to a community of openly greedy, grasping entrepreneurs, for most of whom the truth is nothing but an inconvenience, standing in the way of more money. So I'm not 100% sure at this point that there's enough love of the truth remaining in organized science for anything which doesn't come with a financial reward attached to it. I guess we'll just have to wait and see. Well, the answer to the above question is in, and it's clear. And the answer is that if DNA had any of the TN structures, it would have to be isolated as a right-handed superhelix. Why? In order to say why, we must decide how we're going to visualize TN DNA. For the purpose of answering this particular question, it's most convenient to visualize it as Model A, the half-right, half-left structure. Model B is topologically the same, only here the distribution of right-handed and left-handed turns is different. There is no reason to presume, however, that the energetics with respect to tertiary winding will be different simply because the right-handed and left-handed portions are not segregated into separate regions. Model A, topologically speaking, is 50% left-handed, which cannot change unless a swivel is created by the rupturing of at least one covalent bond in the sugar phosphate backbone. What do we know about left-handed DNA? We know that the left-handed helix, or the Z form of DNA, does not normally occur in natural linear DNA of average base sequence, but only in certain synthetic copolymers. Therefore, there is no reason to doubt that DNA, under physiological conditions, will assume the Watson-Crick right-handed helical structure whenever possible. Here, however, it is not possible because the left-handed portion is locked in at the time of creation. We must therefore conclude that a chromosome constrained to be 50% left-handed in the absence of the nuclear proteins necessary to support this structure will be topologically unstable and will do whatever it can to convert to a 100% right-handed helix. And what can it do? The left-handed secondary turns are locked in and cannot be removed. Only one option remains. It can take on right-handed tertiary superhelical turns, each of which unwinds one of the unwanted left-handed secondary helical turns. In the 1,000-fold oversimplified drawing shown here, the bottom of the chromosome has exactly 4 left-handed helical turns. If such a simple structure actually existed, then the mere introduction of 4 right-handed superhelical turns would totally untwist the bottom into a pair of parallel lines, and 4 more superhelical turns would twist it in the opposite direction, yielding a secondary structure which was an all right-handed Watson-Crick helix. I have not attempted to draw a picture of this because we've portrayed it previously with our rope models. In practice, it will be impossible for the molecule to remove all of its left-handed turns because of the problem we discussed earlier, namely that of steric hindrance, which will increase as the number of superhelical turns increases. Picture C depicts, schematically, the equilibrium state beyond which there can be no further supertwisting. The point is that if TN DNA existed, it would have to be a right-handed superhelix, and the extent of right-handed superhelicity would have to be the maximum extent possible, established by an equilibrium between the push of the left-handed secondary helical winding as it tries to unwind, but balanced by the resistance of the structure to very high degrees of superhelical twisting. Let us look once again at our alkali denaturation data, with all the labels and with all the pictures of the various forms. We've added a tightly wound superhelix to the picture portion of the data, now highlighted in purple, and we shall be explaining it shortly. Otherwise, the data is exactly the same data we employed previously from the laboratories of Rush and Warner. Let us now see if we can explain these data without making the assumption that DNA has any net helical twist. As previously, we note that Form 1 sediments more rapidly than nicked Form 2, indicating that Form 1 is superhelical, illustrated in the small drawing above the curve. As we pointed out before, traditional helicists explain this by alleging that DNA, for some strange reason, must be created in an underwound state. TN theory, however, requires no strange explanation, simply noting that the chromosome is 50% right-handed and 50% left-handed, topologically speaking, and that some of the unwanted Z-type left-handed secondary helical turns can, and will, be converted into the more desirable Watson-Crick right-handed helical turns by the formation of right-handed superhelical tertiary twists. As explained previously, this process continues until steric hindrance brings it to a halt. Thus, we have accounted for the first portion of the curve without the need for presuming any topological linkage between the strands. Next, we turn to the pH region of 11.6 to 12, where the S value dips to that of relaxed DNA, indicating that the superhelical turns are removed. Why? It's really quite simple. All observers, both traditionalists and anti-helicists, agree that in this pH range, right-handed DNA becomes less favorable and, in fact, begins to unwind. I don't imagine anyone will be terribly surprised to hear me say that, but now I'm going to show you something you may not have thought of. Left-handed DNA in this pH range starts to become more favorable. I'll show you why momentarily. For now, I'll just say that as the pH increases, right-handed DNA becomes less favorable, and left-handed DNA becomes more favorable, until at pH 11.8, the stability of the two forms becomes equal, and all superhelical twists vanish. Why do I say that at high pH, left-handed DNA becomes more favorable? Although the subject is rarely discussed, it's been known for many decades that the addition of denaturants to linear duplex DNA sometimes causes the direction of helical winding to reverse. That is, the right-handed helical winding converts to left-handed helical winding. I refer to this as an RL conversion. Although there's a rather large literature on this subject now, in 1974, when I began studying it, there were only a few articles. The earliest I found was by Travers et al., 1970, who found an inversion of the ORD, or optical rotatory dispersion, spectrum of DNA in methanol at low temperature. They interpreted this as indicating a reversal of helical winding, that is, an R to L conversion. The same thing was deduced from the inversion of the CD, or circular dichroism spectra, of DNA in high salt, and in the presence of the intercalating agent mitomycin C. Here's some of the data from these authors. The blue arrows show the ORD or CD spectra of the native DNAs, and the orange arrows show the spectral inversions. The significance of these spectral inversions with respect to the proposed R to L conversion was, in those early days, questioned by some, but in the process of time, subsequent publications provided further evidence that DNA, under these conditions, was indeed left-handed, culminating in Alexander Rich's X-ray crystallography studies, which elucidated the so-called zDNA left-handed form. What do alcohol, salt, and mitomycin C have in common? Chemically, nothing, but each causes unwinding of DNA. It would appear then that anything which unwinds DNA might produce an R to L conversion. Can such a thing be explained? Again, the explanation is really very simple. It lies in the structure of zDNA. Let's look at it. Look how pretty it is from the top. Now let's look at it in 3D. By the way, this is one movie in which it really matters which way your eye perceives the molecule to be spinning. You should see it spinning to the right, and the direction of helical winding will correctly appear to be left-handed. If, however, your eye is playing that perspective trick on you, then it will appear to be spinning to the left, and the direction of helical winding will seem to be right-handed, which is backwards. If this is what you see, just keep looking at it, and eventually it will change direction. Here's an accurate drawing of 12 base pairs each of classic right-handed bDNA alongside left-handed zDNA. Please note that zDNA is significantly longer. In other words, relative to the right-handed double helix, it's less tightly wound. This is critical to our understanding of the behavior of circular DNA, so let's look at the actual numbers. The rise per residue for zDNA is 3.7 angstroms, whereas for classic bDNA, the rise per residue is only 3.4 angstroms. zDNA has more residues per helical turn and a much larger pitch. At the bottom of the slide, I've shown a comparison of the lengths of the two forms for a segment of 12 base pairs, which reveals that zDNA is 4 angstroms, or about 10% longer. Looking at these numbers, we can see immediately why all those different agents cause an R to L conversion. zDNA is a more loosely wound helix than right-handed DNA. The base pairs are stacked 10% further apart, and the pitch is 45 angstroms, which is 34% longer than the pitch of right-handed DNA. No one has ever seen a Watson-Crick right-handed structure with such wide spacings, which presumably doesn't exist. Therefore, we may be well justified in assuming that anything which causes a 10% unwinding of DNA will precipitate an R to L conversion, since only the left-handed form is known under such conditions. Here's an animated drawing which dramatizes this concept. Note the length scale we used earlier, where each unit of length equals 34 angstroms, the length of one Watson-Crick turn. Against this scale, we can see immediately that the Z form of DNA is clearly stretched out, i.e., more loosely wound. One picture tells 1,000 words. When bDNA unwinds to the point of having the same length as zDNA, it becomes zDNA, because at that pitch, right-handed DNA does not exist. That is, when the DNA has unwound to the point that the base pairs are 3.7 angstroms apart, where the only known structure is the left-handed Z structure, the DNA will undergo an R to L conversion. Now we can return to the alkali denaturation titration curve. Backtracking for a moment, I will reiterate that at physiological pH, the native chromosome is more dense than nicked circular or linear DNA because it takes on right-handed supertwists in order to unwind some of the unwanted left-handed secondary twists. As the pH approaches 11.8, the relative stability of the right and left-handed forms becomes equal, and all the supertwists come out. At this point, the S values for all forms of circular DNA, both intact, nicked, and even single-stranded circular DNA, are essentially the same, because they all sediment in relaxed form, as open circles. As the pH increases beyond 11.8, the right-handed twists start to unwind in earnest. At this point, the left-handed form actually becomes more stable than right-handed DNA, and we start to see supertwists in the opposite sense, namely left-handed supertwists, each of which unwinds the now undesirable right-handed helical twists. Note in the drawing above the curve that the direction of superhelical winding has now reversed. The behavior of DNA in this pH range is non-controversial, and is explained in the same way by both traditional helicists and us troublemaking anti-helicists. This process of left-handed superhelical twisting continues up to the point marked high around pH 12.2, at which pH it has been reported by several authors that the DNA finally denatures with a loss of all hydrogen bonding. Let us pause for the moment and look at nicked DNA, i.e. Form 2. This is the blue data at the bottom of the graph. We are now in a position to address one of the rarely discussed aspects of these data, namely that the Form 2 curve coincides with the Form 1 curve from pH 11.8 up to pH 12. At this latter pH, Form 2, but not Form 1, splits into its components, namely single-stranded circular DNA and single-stranded linear DNA. What's the meaning of this upward sweep of Form 2, following Form 1, when Form 2 is supposed to be free of topological constraints, being nicked? How can this be explained? Standard Watson-Crick theory offers no explanation for this, and it's never discussed. We can explain it here, however. In TN theory, we note that as the pH rises above 11.8, the Form 2 chromosome begins to unwind. Remember that Form 2 is entirely right-handed, since the nick acts as a swivel, allowing the chromosome to assume the most stable conformation, that being the standard Watson-Crick structure. As the pH increases, however, and the longitudinal base pair spacing increases from 3.4 angstroms to 3.7 angstroms, the chromosome takes on more and more left-handed superhelical twists for the same reason Form 1 does so in the same pH range, namely because left-handed supertwists convert the right-handed secondary twists, which have now become undesirable, into left-handed secondary twists. What happens at pH 12? Because no one in this field seems to care about this portion of the curve, we therefore lack data to answer this question with certainty. That doesn't mean, however, that we can't take a good educated guess. It may be simply that at pH 12, base pairing is so weakened that the duplex cannot survive, being held together, as it normally is, by hydrogen bonds. I would strongly opine, however, that it is more than that. The fact that Form 1 survives up to pH of about 12.3 indicates that base pairing, i.e. hydrogen bonding, still exists in the pH range 12.0 to 12.3. Look at the purple arrows here. They show the range within which Form 2 no longer exists, but Form 1 persists. Clearly, there are still at least weak hydrogen bonds in this pH range, or Form 1 would also denature. With respect to Form 2 nicked DNA, I suspect that at pH 12, the beginning of this pH range, the advanced degree of unwinding causes the base pairs to reach the critical 3.7 angstrom spacing, which is incompatible with a Watson-Crick structure. This gives rise to a sudden cooperative R to L conversion. The chromosome, as a duplex structure, does not survive this maneuver because base pairing at pH 12 is so weak that the centrifugal force of the spinning chromosome drives the strands apart. Here's an admittedly silly effort to portray this in a movie. I'm the so-called artist for most of these slides, and I don't have the graphic ability to portray the spinning duplex, so in lieu of that, I settled for just making it shake around. Keep in mind, however, that denaturing DNA spins, and that the force I'm trying to portray is centrifugal force. All right, we've seen that the strands of Form 2 split apart into single-stranded linear and circular forms at pH 12. If, as I've asserted, the strands of Form 1 are topologically non-linked, that is TN, why don't they also split apart at pH 12? There are at least two reasons for this, one fairly obvious, and the other somewhat subtle. The obvious one is that Form 1 has no free ends. Denaturation of linear or nicked circular DNA is considered to be a cooperative process, which starts slowly with the separation of a critical number of base pairs at a free end, thereafter proceeding rapidly with the entire duplex structure opening up like a zipper. Form 1 has no free end to be the site of the initial strand separation event, and it's therefore protected to some extent from denaturation. Can we estimate the magnitude of this protection? The top of this slide depicts a DNA duplex with a single nick, and therefore 2 free ends. In order to initiate denaturation, a disruptive force must be applied, depicted here in caricature as a 100-pound weight which must be lifted up. This force must be applied to either one of the 2 free ends. Keep in mind that a nucleus of disrupted base pairs sufficient to initiate denaturation only need be obtained at one of the 2 free ends, since denaturation, once initiated, will spread rapidly along the entire length of the DNA. Now look at the bottom of the slide. To initiate denaturation in the absence of a free end, a force of twice the magnitude must be applied, as the diagram should explain without the need for 1,000 words. If the denaturing force is high pH, i.e. hydroxide ions, then we may, as a first approximation at least, consider this to correspond to a doubling of the hydroxide ion concentration, or, on the logarithmic pH scale, an increase of 0.3 pH units. Looking back at our alkali denaturation curve, we see that the denaturation pH of Form 1, known to be about 12.3, is in fact approximately 0.3 units higher than that of nicked Form 2. Coincidence? I guess you'll have to decide for yourself. As I said earlier, there is another, more subtle way to approach this same question. Since Form 1 is a base-paired structure, and since it survives up to pH 12.3, it follows that there is some hydrogen bonding, albeit weak, in the pH range of 12 to 12.3. It is therefore possible in principle for nicked Form 2 to also survive as a duplex up to pH 12.3, but it doesn't. This is why we have proposed that an R to L conversion at pH 12 provides sufficient extra disruptive energy to cause strand separation at the lower pH. The subtle question is, why don't the strands of Form 1 also undergo a rapid change in the direction of helical winding at pH 12 and separate at that lower pH as the strands of Form 2 do? The answer lies in topology. Let us look again at this not very likely, but very educational version of a TN chromosome. If you examine it and think about it, or even better, simply make a model by twisting together 2 rubber bands, you will see immediately that when DNA has the TN structure, every addition of a right-handed turn must be accompanied by addition of a left-handed turn, and every removal of a right-handed turn must be accompanied by removal of a left-handed turn. Speaking anthropomorphically, at pH 12, even if Form 1 wanted to convert to the all left-handed form, it couldn't, because every right-handed turn unwound would have to be accompanied by the unwinding of a left-handed turn. But in the pH range between 12 and 12.3, left-handed DNA is not only possible, it is favored, and therefore the 50% of the chromosome which is topologically left-handed, desiring to increase, not decrease, will oppose any removal of helical turns at all. In fact, if we look at the denaturation curve for Form 1, now highlighted in purple, we can see that the only way Form 1 can remove right-handed twists without also removing left-handed twists is to become increasingly superhelical in the left-handed sense. Note the tremendous increase in S which accompanies this, the density of the chromosome quite evidently increasing by 100% in the pH range of 12.3 to 13. Now look at the pictures I've superimposed on the data. All writers on this subject agree with the first three pictures. But what about the fourth picture? What is the structure of DNA above pH 12.3, and why don't the strands separate? Concerning the exact structure of denatured Form 1, known as Form 4, no one seems to care. I've never seen a word written on the subject. As for the question of why the strands don't separate, traditional helicists have their very strongest argument here, one which has, in all probability, been the backbone of all resistance to TN theory for over 30 years. They simply fall back on the obvious fact that in a Watson-Crick duplex which is covalently closed into a circle, the strands are topologically locked together. Why should they separate? Why indeed? But wait a minute. We still don't know the structure of Form 4. Is it possible that the failure of the strands to separate at high pH is due to some unforeseen structural property of Form 4, having nothing to do with topological linkage? Anyone who counts himself a champion of the Watson-Crick structure will say that my back is up against the wall on this portion of the curve, and he would be right. But guess what? I went through the seemingly hopeless task of considering the question, and not only is there an answer, but it's a darn good one. So good, in fact, that it's hard for me to believe that it isn't true. I may be the only scientist in the world who gives a damn about the structure of Form 4. Remember this slide, which I showed before? This is the establishment view of Form 4 structure, described by Bill Strider, one of the world's leading experts on it, as, quote, a tangled mess. That's almost like saying it has no structure at all, but its properties hardly support this view. Look again at the curve for renaturation of Form 4, highlighted in purple. It forms at high pH, but when the pH is restored to normal, the original properties are not restored. With a sedimentation coefficient of about 36S, it remains 50% more dense than the native Form 1, which has a sedimentation coefficient of only 21S. This behavior contrasts sharply with that of calf, thymus, or other linear DNA, which can be denatured by boiling and reannealed by slowly cooling. Intact circular chromosomes cannot be heat denatured at all, and when alkali denatured, as shown here, they do not reanneal when the pH is normalized. When this was first discovered in the 1960s, Form 4 was dubbed permanently denatured DNA. Robert Warner, a highly respected scientist who chaired the biochemistry department at UC Irvine for many years, got interested in Form 4 as a vehicle for purifying viral DNA. Because of its extreme density, he reasoned that it would be a cinch to separate it from other proteins and nucleic acids. This, however, required that there be a way to convert the Form 4, once purified, back to native Form 1. Most of the laboratory work on this project was done by the above-mentioned Bill Strider, who was a doctoral candidate at the time. Subsequently, Warner continued to refine the work, with an almost maddening precision, for another decade, but Strider's results continue to define the problem sufficiently for our purposes. Follow with me, if you will, some of these data. Form 4 was prepared by alkali denaturation of the replicative form, or RF, of the chromosome of the virus Phi-X174. The DNA in buffered 1 molar sodium chloride was subjected to many different combinations of pH and temperature, as shown. The percent renaturation, i.e. back to native Form 1, was measured. Note that at any temperature of incubation, there was only a single narrow range of pH within which renaturation was rapid and complete. For example, please look at the first curve labeled 70 degrees, 2 minutes. What these data mean is that at a pH of 10.7, 100% renaturation occurred in only 2 minutes. But lowering the pH a mere 1/2 unit to 10.2 almost totally wiped out all renaturation. I think you can mentally extrapolate these data to the physiological pH range of about 7, and it's easy to see that at physiological pH there would be no measurable renaturation under these conditions. This is true for all 6 curves shown. And if we lower the temperature to room temperature, that is 25 degrees, it was difficult to get any reannealing at any pH. Even at the elevated pH of 12, it took an hour to get less than 50% of the form 4 to reanneal back to form 1 at room temperature. At each temperature, there was only a single narrow band of pH within which renaturation occurred rapidly and efficiently. Moving to the right side of the slide, you can see that decreasing the temperature raised the pH optimum. But the fastidious requirement for exact adjustment of pH, temperature, and ionic strength is evident under all circumstances. Does this strike you as the behavior expected for a random coil of structureless, collapsed DNA, a tangled mess, as it has been called? Or, on the contrary, is this a sign of a very highly ordered structure? I would strongly suspect the latter. But what structure? Let's look back to the alkali titration curve with the alkaline end of the form 1 curve highlighted in purple and see if there are any clues. Although there's a shoulder in the form 1 curve at chi, the general shape of the curve might be construed to suggest that there is no enormous conformational change between pH 12.3 and 13. Other than the shoulder at chi, the curve just proceeds upward in an uncomplicated, orderly, and nearly linear fashion. It is not controverted by any writer on the subject that circular DNA becomes a left-handed superhelix above pH 11.8, represented here by the highlighted picture behind the curve. All agree as well that the explanation is the unwinding of right-handed secondary helical turns, which forces the chromosome to assume the left-handed superhelical conformation. It is also not controverted that by pH 12.3, that point labeled chi, the superhelical twisting has progressed to the point that the superhelix density is the same as that of the native chromosome, only with the superhelical twisting now in the opposite direction. I would propose that as the pH increases past 12.3, the superhelical twisting simply continues to increase, as per the highlighted drawing, with water being progressively squeezed out of the core, culminating in a highly supertwisted, relatively anhydrous structure. Why do I say this? We need to ask what sorts of structures are possible for the chromosome at these high pHs. Well, how can 2 strands of DNA interact? The possibilities are not unlimited. First of all, we must take into consideration that at high pH, the structure becomes in effect a 4-stranded structure. Look what happens as left-handed supertwisting progresses. 2 duplex strands from each side of the formerly circular chromosome get twisted closer and closer together until 4 single strands lie much closer together than ever occurs at neutral pH. What structures are possible here? Structures built around base pairing can be excluded because at highly alkaline pH, the atoms involved in base pairing will all be deprotonated. Base stacking remains possible, but I know of no precedent for a 4-stranded structure at high pH involving what would have to be a virtually random pattern of stacked bases. But there is a well-characterized structure which could pertain in this case, and I'm going to propose that it appears at high pH because I can't think of any reasonable alternative. It is the structure originally proposed by Linus Pauling about a month before Watson and Crick published their double helix structure in 1953. Prior to Watson and Crick's 1953 publication, No one knew how the structure of DNA was going to reflect DNA's role as the bearer of genetic character for all life, specifically the structural counterpart and genetic significance of the molar equivalence between adenine and thymine and between guanine and cytosine was not known. Lacking this information, Pauling could only propose a structure which was consistent with the rules of chemistry, concerning which he was the acknowledged world master. Based upon the principles of chemistry, Pauling put the phosphate groups on the inside and the bases on the outside. As the vast number of phosphate crystalline compounds in the world demonstrates, phosphate groups like to line up, bound together by salt bridges. If you're old enough to remember, you undoubtedly will not have forgotten Pauling's world-famous blunder, immortalized by Watson in his popular book, The Double Helix, of putting hydrogen bonds in the inside instead of salt bridges. Of course, Pauling really meant salt bridges. It was the scientific equivalent of a slip of the tongue. But upon publication of the Watson-Crick structure in Nature, quite evidently embarrassed by the whole affair, Pauling quit all work on DNA forever. That's too bad, because I think he was right. He didn't deduce the structure of DNA in the normal state, but it seems to me that he inadvertently discovered the most probable structure for DNA in the denatured state. Although Pauling gave the world a three-stranded structure, as illustrated in his drawings here, he stated in his writings that a four-stranded structure was even easier to assemble. He chose the three-stranded model only because he was better able to make it fit Wilkins' X-ray data. In other words, the Pauling structure for DNA, long forgotten, is in fact the perfect structure for Form 4 circular DNA, where the denaturation process brings four strands of DNA into unusually close approximation because of extreme supertwisting under conditions of high pH where base pairing is ruled out. I should note, for the benefit of those not familiar with the variety of structures found in viruses, that examples are known of viruses whose DNA consists of a helix with the phosphate groups on the inside. Lauren Day of the New York City Department of Public Health Labs has discovered two such viruses and provided a detailed molecular structure for one of them. Now here are some pictures of what a small section of a Pauling Form 4 quadruple helix might look like. This model was made by simply taking 4 DNA strands and spacing them to allow for 3 angstrom salt bridges. And here's a movie of the same structure. It has a nice, orderly appearance, which is exactly what you'd expect for a structure which displays the fastidious behavior known for Form 4. I would propose this as the structure for Form 4, even if I believe that native circular DNA was a helix, which I don't believe. But it would appear to me that the time has come to stop pretending that Form 4 is a tangled mess, and to face the fact that it has to have some structure of some sort. If not this, then what? What other structure is possible? I can't think of any. This completes our review of the alkaline titration curve for Form 1 native circular DNA. We have shown that these data can be very satisfactorily accounted for by the TN theory, which states that the strands of circular DNA have no topological linkage. But even though the TN theory makes sense and is consistent with what we know about circular DNA, that doesn't make it true. What evidence is there that this structure exists in the real world? Over the decades, I've been repeatedly criticized for failing to take note of a veritable mountain of evidence proving the Watson-Crick structure. Oddly enough, however, when I demanded to be shown this mountain, the critics either became mute or made reference to only a tiny group of manuscripts, 4 to be exact. So the mountain appears to be a molehill. We shall look at these papers shortly, but first I must tell you which types of papers do not provide direct evidence for the Watson-Crick structure. There are innumerable papers which deal with DNA topology, and people naively presume that these somehow prove that DNA is a helix. The only reason they assume this is because they're either too disinterested or just too darn lazy to think the problem through. We shall not have that luxury here. These papers are exemplified by the work of J.C. Wang at Harvard, who scrupulously investigated the effects of various agents and conditions on DNA superhelicity. This means counting changes in numbers of superhelical twists and relating the changes to the oft-referenced topology formula Lk equals T plus W. This equation is no more than simple grade school arithmetic. Lk is the so-called linking number, the number of times one strand crosses the other when the chromosome is forced to lie flat in a plane. In the picture on the left, we've forced the chromosome to lie flat by employing imaginary thumbtacks. As long as the chromosome remains intact, Lk never changes. It's a topological parameter which is permanently locked in at the moment of the chromosome's creation, and it can only be altered by breaking open a strand, changing the winding, and then resealing it. When we remove the thumbtacks, however, the winding changes, and we get the picture on the right. According to traditional Watson-Crick theory, what's happening here is that the chromosome has become super twisted to compensate for the alleged underwinding in the secondary structure. In the end, we have a new winding number, T, which stands for twist. Regardless of how underwound, or for that matter, even overwound, the native chromosome may be, under physiological conditions, T will generally be assumed to always be the standard Watson-Crick number, or exactly 10 base pairs per full helical twist, with a pitch of 34 angstroms. This is the structure DNA prefers, and if it's not present in the native chromosome, the chromosome will superhelically twist to bring it about. These super twists are enumerated by the letter W, which stands for writhe. The relationship between Lk, T, and W is precisely the same relationship we obsessed about with our rope models earlier. It's a very simple arithmetic relationship as per the equation Lk equals T plus W. In order to make this simple arithmetic formula work, the sense, or direction, of superhelical winding must be defined such that right-handed supertwists are negative and left-handed supertwists are positive. Let's consider the topology equation for a typical small virus or plasmid chromosome, such as Phi-X174RF, which has some 5,000 base pairs. If a segment of DNA of this length is linear, it will have the standard Watson-Crick helicity, that is, 10 base pairs per helical turn, or a total of 500 secondary helical twists. If, however, as traditionalists insist, the circular Phi-F174RF chromosome is created in the underwound state, then Lk will be less than 500. How much less? Well, the number of supertwists can be estimated from experiments, including direct electron microscopic observations, and it's found to be about 25. Their direction is also known. Since intercalating agents decrease the absolute value of the number of supertwists, it can readily be deduced that the supertwists are right-handed or negative in value. As I hopefully showed you with the rope models, the deficiency in the number of secondary helical twists must be exactly the same as the number of supertwists, so that the mathematics is totally simple. Lk equals T plus W equals 500 minus 25. So, Lk equals 475. We thus learn from the topological equation that the native chromosome is underwound by 25 Watson-Crick twists, or 5% underwound. All this assumes that the chromosome has the Watson-Crick structure. What if it actually is in the Tn topologically non-linked conformation, as I and a goodly number of others believe? What becomes of the topology equation? Numerous studies by researchers such as Wang measure changes in superhelicity in the presence of various physical and chemical agents. These sorts of studies form a very substantial part of the so-called mountain of evidence in support of the Watson-Crick theory. What if DNA turns out to not have the Watson-Crick structure? Do these studies have to be discarded? The answer is no data has to be discarded, and very little has to be done to the topology equation. If DNA has no net helical twists, being topologically 50% right-handed and 50% left-handed, then LK actually has a value of 0. For a chromosome the size of phi-X174 with 5,000 base pairs, since we previously presumed LK to have a value of 475, we need only subtract 475 from both sides of the equation to correct the error, giving us the admittedly somewhat silly-looking new topological equation shown in the slide. Note that after subtracting 475, we wind up with the somewhat trivial-looking equation 0 equals 25 minus 25. Obviously, in this case, the equation no longer serves much purpose, but it's still true. What it's now saying is that since the flattened chromosome on the left is exactly 50% right-handed and 50% left-handed, with LK therefore having a net value of 0, the parameter t in the drawing on the right now represents any excess of either right-handed or left-handed twists above 50%, and must be exactly and precisely equal to the number of supertwists, W. In more complex language, we might say that every right-handed or negative supertwist adds, in one-to-one fashion, a single right-handed twist to the secondary winding. Conversely, every left-handed or a positive supertwist removes a right-handed twist from the secondary winding. All this is merely a long, drawn-out way of pointing out that the data of Wang and numerous others like him do not need, if I may be permitted a medical analogy, emergency surgery if DNA turns out to not have the Watson-Crick structure. They merely need a slight chiropractic adjustment with respect to interpretation. What about papers which directly investigate the LK of the native chromosome? As I've already said, there are really only 4 such papers which have ever been quoted, far more of a molehill than a mountain. The first pair of papers, by Sebring et al. And Yanish et al., reached the conclusion that DNA is a helix through observations of the electron micrographic appearance of replicative intermediates of small circular chromosomes. This drawing, which is artistically dreadful but topologically accurate, illustrates their observations. The parental loop of unreplicated DNA is observed to be superhelical, and the pair of daughter loops are relaxed, or open circles. This, we are told, proves that DNA is a helix. Huh? Where's the logic here? The fact that the daughter loops are open circles is consistent with the fact that they have not yet been sealed shut. But what does the superhelicity of the parental structure prove? The logic is obviously bizarre, and we've already gone over it previously. It goes something like this. DNA must have the Watson-Crick structure because no other structure is possible. Circular DNA with a Watson-Crick structure is invariably superhelical. Therefore, anything which is superhelical must have the Watson-Crick structure. Am I wrong? I don't think so. They're saying that since DNA must have the Watson-Crick structure, it therefore has the Watson-Crick structure. This is just Planet of the Apes again. I've gone to a lot of trouble to show you that a topologically non-linked chromosome would undoubtedly have a goodly number of right-handed supertwists. Not only does the TN theory explain the superhelicity of native DNA, but it explains it without making silly assumptions, such as the unwarranted assumption that DNA, for some mysterious reason, is underwound. Since the conclusion reached from these electron micrographs of replicative intermediates is that DNA has the Watson-Crick helical structure simply because it's superhelical, which is logically absurd, you can perhaps now see that this sort of research proves absolutely nothing. It's not a mountain. It's a molehill. Here is a reminder of what we discussed in great detail earlier. You'll need to keep this in mind as we move to the next paper. It's also worth belaboring the point that in the living systems in which DNA is found in nature, there are invariably basic proteins present, which certainly play an indispensable role in maintaining the normal architecture of DNA in vivo. It's only when these proteins are stripped away in vitro that the differences in the relative stability of right-handed and left-handed DNA cause superhelical twisting. In terms of pervasive influence, the most thought-suppressing, creativity-destroying paper on this subject was by Crick himself. The circular logic employed in the above-referenced studies of replicative intermediates was used again by Crick in this paper. However, Crick's stature in this field was so huge that once he said it, it became the law, and almost no one dared to challenge his conclusions afterwards. Let's examine Crick's false logic to see where he went wrong. In considering the title question of his article, "Is DNA really a double helix?" he came to the conclusion that the best evidence was from topoisomerase experiments. Topoisomerase both nicks and reseals circular DNA. Whenever it nicks the DNA becomes relaxed. All tightly wound superhelical structures will immediately unwind, and the chromosomes will assume the all right-handed Watson-Crick structure. But they will not necessarily adhere precisely and exactly to the Watson-Crick winding number of a single 10 base pair helical turn per 34 angstroms of length. During the period that they're in the nicked state, random thermal motion in the medium will cause changes in the winding, so that when the molecules are resealed, there will generally be some small but significant number of supertwists, according to the topology equation we just discussed. Note that since the superhelical winding is the result of thermal buffeting of the chromosome, the direction can be either right-handed or left-handed, i.e., the random thermal motion in the medium might, at one point in time, bring about a small degree of unwinding of the Watson-Crick structure, but a moment later it might bring about a small degree of overwinding. The first will cause the appearance of right-handed or negative supertwists after the molecule is resealed, and the second will cause the appearance of left-handed supertwists. Now, if DNA is treated with topoisomerase to equilibrium, a family of so-called topoisomers will be seen on gel electrophoresis of the steady-state product. This drawing qualitatively depicts this steady state accurately, with the DNA structures represented by the various bands drawn adjacent to them. The direction of migration in the electric field, as indicated by the arrows, is up. The different bands represent different topoisomers, which differ by one twist in their superhelicity. The slowest band, now highlighted at the bottom of the slide, is totally relaxed DNA, which has been nicked by topoisomerase and has coincidentally been sealed with exactly and precisely the standard Watson-Crick pitch of 10 base pairs per 34 angstroms of length. It has no overwinding or underwinding issues, and it therefore has no supertwists. Just above it, migrating just a little bit faster than it, are the minimally supertwisted forms, i.e., topoisomers containing only one or two supertwists. Note that the direction of supertwisting, that is, whether the supertwists are plus or minus, does not matter in this experiment. A topoisomer with plus 2 superhelical twists will have about the same density as one with minus 2 superhelical twists. Note also that the bands are close together at the bottom, because the difference in density between topoisomers having low degrees of supertwisting is not great. The bands do not become well separated until a larger number of superhelical twists is present, as depicted by a single exemplary topoisomer in the middle of the drawing. At the very top of the drawing is the native chromosome, untreated by topoisomerase, added as a marker. The most highly supertwisted enzyme-generated topoisomers band just beneath it. As at the bottom of the gel, the bands at the top are not very well separated because the difference in density between topoisomers having 24 or 25 supertwists is not great. Now, how does Crick conclude from this data that native DNA is a helix? His words, verbatim from his manuscript, are, quote, "No other interpretation of the bands is even remotely plausible." What does this mean? Well, it doesn't mean what he'd like you to think it means. In order to understand this, we must go back a few paragraphs in his manuscript. He points out, correctly of course, that the strands of plasmids do not separate when alkali denatured, which, he says, proves that they are topologically linked. Note that this is supposed to be the conclusion of the manuscript, but we see here that it's the underlying assumption, raising the question of what the purpose of this manuscript is in the first place. I hope that if I've shown you anything at all, it's at least that alkali denaturation data do not necessarily prove that the strands of circular DNA are topologically linked. The alkali data which Crick specifically quotes to persuade you that DNA is helical are from the very same papers we have used to show that it might not be helical after all. Obviously, more research is needed, but no useful new research appears in this Crick paper. Yet essentially everyone who read it thought what he wanted you to think. And this is what that is. 1. The DNA of a typical 5,000 base pair plasmid is a right-handed helix, since the strands do not separate at high pH. 2. This DNA has 25 superhelical twists, and therefore must have been sealed shut in the 5% underwound state. 3. The agarose gel of the products of topoisomerase treatment reveals something like 25 bands, corresponding to 25 topoisomers, each of which evidently contains one less superhelical twist than the one in front of it in the gel. Finally, 4. Since this is a perfectly good explanation for the bands, we may conclude that DNA is a helix. Do I have to tell you that this is nonsense? Number 1 is presumptuous. Whether or not DNA is helical is what we're supposedly investigating, and here he tells us it's already proven. Number 2 is presumptuous, since it also presumes that DNA is helical, and fails to consider the possibility that there might be other explanations for the 25 superhelical twists. Number 3, and number 3 only, is true, but it proves nothing about the native structure, since it explains only the differences between products of enzyme degradation of the native structure. Number 4, disguised as a so-called conclusion, is in fact not a conclusion at all. It's merely the unjustified starting presumption in number 1, regurgitated as if it was a conclusion. Here's a slide which is sure to offend many, but not anyone possessed with even rudimentary wisdom. Yes, you've learned how to throw genes into huge vats of E. coli, and lo and behold, money comes out of the other side. But you have no idea what's actually going on in those vats, do you? In case I'm not getting through to you, let's take only a moment to predict the outcome of the topoisomerase experiment according to the TN theory. We have to do this because Crick says no other interpretation of the bands is even remotely plausible. Well, we're going to give another interpretation. We start with a native chromosome, which is highly supertwisted, as I've explained and re-explained. If you still don't get it, then I failed as an educator. But the native TN chromosome is supertwisted all the same, whether or not you understand it, and whether or not I failed in my attempts to explain it. As soon as it's nicked by topoisomerase, it totally relaxes. From this point forth, it makes no difference whatsoever what the state of helicity, or lack thereof, of the starting product was, because it's no longer present in the reaction mixture. As the topoisomerase reaction reaches equilibrium, the other topoisomers are generated. If you can't understand that this Crick paper is a sham, then you're missing something essential to the pursuit of real knowledge. And you really need to get back to the lucrative but mindless world of applied biotechnology for profit. Don't worry. In the money-obsessed world we live in today, no one will fault you for loving wealth more than truth. This brings us to our final paper on this subject, namely Stettler et al., from the laboratory of Charles Weissman. Weissman was a co-founder of Biogen, a company with billions of dollars in annual sales. He was one of the first to become very adept at throwing genetically valuable enzyme genes into vats of E. coli and other trained unicellular organisms, and extracting from those vats lucrative gene-engineered products for international sale and distribution. As I've already opined, however, these commercialists haven't a clue as to what actually goes on in the nuclei of these trained animals, at least not from the structural point of view. Nevertheless, we cannot ignore the Weissman paper, even though essentially no one ever cites it, because it was the final nail in the coffin of common sense among those molecular biologists who should have cared about the structure of DNA. I often wonder whether anyone but me ever bothered to really read it. Certainly the editors of JMB didn't read it, or if they did, they must have been half asleep. There is history behind this paper. According to my older and wiser colleagues, Francis Crick was visibly upset by the commotion started by the publication of the Rodley and Saccharin side-by-side structures. He apparently felt personally threatened and put out a public call for a response. The suggestion he made at that time, namely the late 1970s, was that someone, anyone, should prepare complementary single-stranded circular DNA and reanneal it. Let's introduce some terminology immediately. The separated strands of duplex circular chromosomes are often referred to as the plus and minus strands, respectively. Since Crick was sure DNA had the Watson-Crick structure, and since reannealing of separated plus and minus circles couldn't possibly give rise to a topologically linked structure, such as the Watson-Crick structure, Crick was confident that the reannealed product would promptly be shown to be abnormal in its physical properties, and the side-by-side structure could be laid to rest. Two scientists took up the Crick challenge. One was Robert W. Chambers, who at that time was the acting chairman of the biochemistry department at the New York University School of Medicine. Chambers assumed the chairmanship upon the retirement of Severo Ochoa, the man who had won the 1959 Nobel Prize for his discovery of polynucleotide phosphorylase, with which he was able to crack the genetic code. Chambers was a highly respected scientist, best known at that particular time in his long career for elucidating one of the first three-dimensional structures for a transfer RNA. His colleagues referred to him as Bullet Bob because he was sharp as a whip and he never made a mistake. I knew Chambers quite well, since this was the department in which I earned my doctorate degree in biochemistry. If not for this, Chambers' greatest discovery would never have been known, because he chose not to publish it, and I alone have struggled to keep it from sinking into the depths of obscurity. The other man to take up the Crick challenge was Chambers' colleague of many years, Charles Weissman. Weissman had only recently left NYU, where he had been a professor of biochemistry, to found Biogen. In doing so, he'd placed himself in the vanguard of those who have renounced the ancient wisdom, which teaches that striving for knowledge and striving for money are incompatible. Now, we are told, they're suddenly compatible. Ever since then, it has become progressively more difficult for anyone who is not wealthy, through public stock offerings, to get anyone to listen to him or take him seriously. This is an extremely dangerous trend, and one for which the world will, in the end, pay a high price, since money destroys all truth. The Weissman experiment, which was all but directly commissioned by Crick, was in effect uncontrolled, and the conclusions in the discussion section were not supported by the data which was presented. I can't review the entire paper here, but I can cover the main points. The overall experimental design was to kill all interest in Rodley's side-by-side structure and any other topologically non-linked structures by intentionally creating such a structure and proving that it did not have the physical properties of normal DNA. This is illustrated in the slide, the top of which shows my rope model of two separated single-stranded circular half chromosomes. Weissman proposed that they should be reannealed, giving rise to a base pair duplex product as shown in the top right panel. He then proposed to study the physical properties of this product to prove that it was not normal DNA, but something entirely different. Note that the Watson-Crick double helix cannot arise in this experiment, because the separate single strands we start with cannot become plectonemically entwined unless they are broken open, wrapped around one another, and then resealed, something which is not going to be done in this experiment. The duplex product here can only be topologically non-linked. Thus, if it has normal physical properties, then DNA is topologically non-linked. Otherwise, tN-DNA is excluded as a structure for normal DNA. Here's the experimental protocol. DNA from either the plasmid P-beta G or the virus PM2 was nicked with DNase-1 under conditions designed to introduce about 1 nick per chromosome. Two identical chromosome substrates are depicted schematically on top of the slide, each containing one blue strand and one red strand. Two purple arrows show the effect of random cleavage by DNase-1, an old-fashioned pre-genetic engineering enzyme which indiscriminately cleaves essentially anywhere on either strand. As indicated by the arrows, in the chromosome on the left, the blue strand has been nicked, and on the right, the other, i.e. the red strand, has been nicked. Having now been nicked, the single strands can be readily separated by alkali denaturation, yielding the products shown on the bottom of the slide. The nicked strand, upon denaturation, becomes linearized. Thus, the chromosome on the left yields a blue linear strand and a red circular strand, whereas on the right we see the opposite, namely a blue circular strand and a red linear strand. The mixture of linear and circular DNA was then sedimented through an alkaline sucrose gradient, which resulted in the data shown on the right side of the slide. The most important peaks, whose identities were confirmed by electron microscopy, were a peak of single-stranded linear DNA and, just ahead of it, a peak of single-stranded circular DNA. Both these peaks were mixtures of DNA from both strands of the chromosome. That is, the slower peak contained a mixture of plus and minus linear strands, while a faster peak contained a mixture of plus and minus circular strands. The fractions enriched in plus and minus circular strands were pooled immediately and reannealed under the following conditions: pH 8.5, temperature 60 degrees, time 20 minutes. Please keep these numbers in mind because we'll be getting back to them shortly. Next, the product was purified and analyzed by gel electrophoresis. Here's one of Weissman's gels showing Form 1 and Form 2 markers on the left, a single-stranded DNA marker on the right, and a peculiar new form of DNA in the middle, designated Form 5. Form 5 migrated faster than Form 1, but slower than single-stranded DNA. What is it? Weissman's stated conclusion was that in creating the so-called Form 5, he had in fact created the true side-by-side structure. That is, a base pair duplex structure whose strands were not plectonemically intertwined. From this slide, we can see that whatever it was that he created, it certainly was not normal DNA, since it had the wrong electrophoretic mobility. This was supposed to prove that the traditional Watson-Crick structure, appearing as Form 1 in the left lane of the gel, did not have the Rodley side-by-side structure. Here's the problem. Keep in mind the pH and temperature at which Weissman did his reannealing, pH 8.5 and 60 degrees. I concede that Weissman created a duplex structure, but was it really a properly base-paired structure? I think maybe not. Bearing in mind that circular DNA is not the same as linear DNA, we may start by asking, are these conditions under which circular DNA will reanneal? To get a handle on this, let's look again at the reannealing data from the masters of reannealing, Robert Warner and his associates. To make this task easier, let's remove all the data except the 60-degree curve. Note there's a pH optimum around pH 11, where there's essentially 100% reannealing in only 10 minutes. As pointed out previously, however, notice that even small changes in pH markedly discouraged reannealing. Thus, at the lowest pH in these data, pH 10.6, reannealing was already getting rather sluggish, with only about 30% reannealing in the time allotted. What do these data predict at pH 8.5, the pH chosen, apparently quite arbitrarily and capriciously, by Weissman for his reannealing? Well, you can't tell unless you extrapolate this data to 8.5. The trouble is, extrapolation of these data quickly take us right off the chart. The extrapolated data line crosses the x-axis at pH 10.4. Note that even at this relatively high pH, the predicted percent reannealing in this experiment is 0%. There would be absolutely no renaturation under those conditions. And Weissman is 2 entire pH units below this. That is, Weissman's supposedly reannealed DNA was created at a pH 2 entire units below the pH of 0 renaturation. What can we conclude from this, other than that incubating DNA at pH 8.5, 60 degrees, would result in no renaturation? And yet the experiment generated some sort of weird duplex product, which the authors called Form 5. What was it? To this day, it remains a complete mystery. Now, those of you who are really astute and observant may be saying at this point that my logic is flawed. You may be asking yourself the following. Since Form 4, although denatured with respect to base pairing, is a structure within which the two strands remain physically associated, what gives Dr. Beagle-Eyes on the right to say that renaturation data for Form 4 can be applied to renaturation of Weissman's single-stranded circles where the two strands are completely separated? That's a good question. Bear in mind, however, that if the strands of Form 1 are topologically non-linked, then so are the strands of Form 4, regardless of the fact that they remain somehow stuck together physically. If so, then the results of a reannealing experiment may not depend so much upon the relative physical locations of the strands at the start of the experiment, but only upon establishment of the precise pH, temperature, and ionic strength required for the optimization of the reannealing reaction. Along these lines, there is one thing which can be said with certainty. Form 1 is a base-paired structure, whereas both separate single-stranded circular DNA and Form 4 are non-base-paired structures. There's got to be a transitional form between them. Denatured DNA must pass through this transitional state if the single strands are to reanneal. I'll say as much as can be said about the transitional state, then show a movie. The transitional state I refer to is a juxtaposition of the two strands, base to base, with a wheel-like rotation taking place, so the proper Watson-Crick base pairs can come into alignment. Without this, reannealing cannot occur. The conditions established by Robert Warner for optimal renaturation are not optimal for the stability of either denatured or renatured DNA, but lie somewhere in the middle. Therefore, I've adopted the arbitrary terminology Form 0 for the transitional form. This is a sort of pluripotent form which, with small changes in prevailing conditions, can lead to any of the other forms. In Form 0, weak base pairs repeatedly form and then rupture. At any given moment in time, such as the moment illustrated here, the odds are that few bases will fortuitously lie adjacent to other bases with which they can form proper hydrogen bonds. Under those narrow sets of conditions which are optimal for renaturation, however, it is both necessary and sufficient to presume that the single-stranded circles are rendered capable of rotating with respect to one another until the complementary base pairs are properly realigned and hydrogen bonding is re-established. Since Weissman's conditions for reannealing were far, far from anything which could reasonably be expected to result in significant restoration of a base-paired structure, what then is this Form 5 stuff? I can't answer this question any better than anyone else, but I certainly can take an educated guess. And my guess is that it's merely Form 4. We know that both Forms 1 and Form 4 can exist over the entire physiological pH scale. But Form 1 requires precise alignment of the bases, whereas Form 4 is totally indiscriminate, requiring only proximity of the two strands. If you're familiar with Form 4 science, you may protest, saying that Form 4 is extremely dense and ought to migrate much faster than the band marked 5 in this gel. I once thought that too, but then I did some research which taught me otherwise. For most of my life, I've had no access to anything even remotely resembling a biochemistry laboratory, but for one brief period of time, a biology teacher named Timothy Purnell, a true gentleman and a true friend of science, made his equipment available to me, and I seized the opportunity to do some research. For several months, I turned my dining room into a lab, which did not ingratiate me to my wife, but which did generate some interesting data. I attempted, during those months, to separate the strands of circular DNA by heating at various pHs and ionic strengths. The long and the short of it is that you cannot heat denature circular DNA under any circumstances, except at pHs so high that it would denature whether or not it was heated. The gel on the left shows a typical experiment from this period. The DNA from the plasmid PUB was a gift from Richard Roberts. Unfortunately, it was not topologically pure, but contained a mixture of Forms 1 and 2, which is visible in every lane except at the highest pHs. The Form 1 band is the one in front, since it is superhelical and moves a bit faster in the gel. At the highest pHs, starting at pH 12.5, we see what may appear to be a widening of the Form 1 band with concomitant fading of the Form 2 band. In fact, the Form 1 band is not really widening, but is merging with a new band of alkali denatured DNA, which fully reveals itself in the final lane at pH 13.4. The single remaining band at pH 13.4 is very faint, reflecting the poor binding of ethidium bromide for single-stranded DNA. Note that all the single-stranded DNA, both single-stranded circular as well as linear, and Form 4, are contained in this single band. We scrupulously study these gels at various times from beginning to end to rule out the possibility that the Form 4 moves so quickly that it might have been missed. But nothing was missed. The Form 4 is definitely in this faint band, mixed with the single-stranded linear and circular forms. The gel on the right is essentially the same experiment, differing only in that the ethidium bromide was incorporated directly into the agarose, whereas on the left, the gels were stained after the electrophoresis was run. With the ethidium bromide incorporated directly into the agarose, the single-stranded band is now split into two bands, revealing its heterogeneous composition. Presumably, one of these bands contains the Form 4, the other a mixture of single-stranded linear and circular forms. Note that Form 4 on these gels moves only marginally faster than Form 1, in sharp contrast to the behavior we saw previously in cesium chloride density gradients, where the Form 4 dropped like a rock. Why? The answer comes from the laboratory of Poels and his group in the Netherlands. These researchers published a series of very important studies on the properties of circular DNA in the 1960s. Shown here is their data concerning the effects of ionic strength on the sedimentation coefficients of the various forms. Look at the Form 4 data. In the physiological range of salt concentration, at the left of the graph, it has the well-known high-density conformation, sedimenting nearly twice as fast as Form 1. But as the ionic strength is decreased, the S value steadily diminishes until, at a salt concentration of 1,000th molar, the S value of Form 4 actually drops below that of Form 1. This is a really fascinating result with obviously important implications for our concepts of the structure of Form 4. But for now, it is sufficient to note that at the ionic strength of a typical agarose gel, indicated by this double-headed vertical arrow, the density of Form 4 is actually quite low. Clearly, this accounts for its surprisingly low electrophoretic mobility in agarose gel electrophoresis. Returning to Weissman's results, we now see that this supposedly new form, which he calls Form 5, may be nothing more than Form 4, created by indiscriminately reannealing DNA under conditions which were extremely suboptimal for the regeneration of Form 1. That is, these were conditions which allowed for an atypical, non-base pair duplex structure to form, but did not allow for the wheel-like rotation which is necessary for the reestablishment of proper base pairing. How about a control experiment? The control experiment is the backbone of the scientific method. Weissman claimed that his Form 5 was a base-paired structure, which is a critically important claim. Therefore, for the control experiment, Weissman used Phi-X174 DNA from the virion, which contains only one of the two strands found in the RF, or replicative form. With only one strand, no Form 5 should appear, if Form 5 is, as he claimed, a base-paired structure. And this was the design of the control experiment. He found a new set of conditions under which DNA from the plasmid P beta G turned into the so-called Form 5, and simultaneously he incubated the single strand of Phi-X174 under the same conditions. He reported that the Phi-X174 remained single-stranded. Therefore, he concluded, the appearance of Form 5 requires the presence of complementary DNA so that there can be specific base pairing. What's wrong with this? A lot. First of all, why did he use a different species of DNA for the original experiment than for the control? He could have generated a so-called Form 5 with Phi-X174 replicative form, which contains both strands of the virus, and then used the virion DNA for his control. But instead, he used DNA from two different species. Very strange. But it gets worse. Much worse. Look at the conditions of incubation of the control experiment. It's not just the DNA which is different. Everything is different. The solvent suddenly is organic, 50% formamide. The pH has been altered. It's now only 8. And the temperature of incubation has been precipitously dropped to 20 degrees. Huh? What's going on here? This is called a control experiment, yet it employs a different DNA in a different solvent at a different pH, at a different temperature, and for a different period of time. What madness caused JMB to publish this? Did anyone even bother to read it? Although the text certainly did not say so, the fact of the matter is that the data, in the form in which it's presented, suggests that Phi-X174 virion DNA did indeed become Form 5 under the conditions of the original experiment, and that new conditions were therefore sought out, where the experimental DNA turned into Form 5 and the control DNA did not. Now, I'm sure that's not the explanation for this data. But if that isn't what happened, then it would be nice if the authors would tell us that that's not what happened. But the paper is silent on this, so we're all left hanging and must draw our own personal conclusions. But there's more still. To prove that Form 5 was a base-paired structure, it was studied by thermal denaturation, which should have revealed a cooperative transition at the melting point. The Form 2 melting curve is normal, revealing the expected cooperative transition at the melting temperature. But the data for the so-called Form 5 reveal essentially no cooperative transition at all upon denaturation, suggesting that Form 5, whatever it is not a base-paired structure. Yet the conclusion of the authors of this paper was that Form 5 is a base-paired structure. What's going on here? And why? Whose idea was this? This brings us to the final chapter in this increasingly annoying story, namely the experiments which prove, or strongly suggest, that DNA is not helical in living systems. We'll start with Bob Chambers, i.e. Bullet Bob. In a word, Chambers inadvertently did the Weissman experiment correctly and got the opposite result. That is, he proved, quite accidentally, that separate plus and minus circles can indeed renature to Form 1. His vehicle was Phi X 174. This was a far more sensible choice of experimental DNA than Weissman's choice, since, as I pointed out above, the Phi X 174 DNA could have been used for both the experiment and the control. As I mentioned earlier, Chambers and Weissman had been colleagues at NYU for years. Chambers knew that Weissman intended to take up the Crick challenge, and he entered the fray as well. It was thus a race. Weissman had more money and more help, and he finished first. The race was over. But Chambers had gotten quite far at the point when he learned, through the biochemistry grapevine, that Weissman's work was accepted for publication in JMB. Chambers had already completed the most difficult part of the work, which was to prepare the mixture of purified single-stranded circles, i.e., the plus and minus strands. So what could he do? He took his painfully acquired single-stranded circles, the products of months of work, and retired them to the refrigerator. About 3 months later, he thought of another, entirely different use for them, but before using them, he decided to subject them to a careful analysis to make sure they were still what they had been when they went into that refrigerator. This analysis began with an analytical velocity gradient centrifugation to determine the sedimentation coefficients of the material present. To his great surprise, he found that a substantial portion of the DNA had spontaneously reannealed back into Form 1. Could it have been Form 5? Remember, Chambers and Weissman knew one another personally for years, and each was well aware of what the other was doing. Remember, too, that it was Weissman's published report on Form 5 which caused Chambers to quit the race. It would therefore be a mistake to presume that old Bullet Bob couldn't distinguish between Form 1 and Form 5. I know from my personal discussions with him that he knew all about Weissman's Form 5, and he was very sure that his spontaneously reannealed form was, in fact, Form 1. So the question was, how did Form 1 get in there? After establishing, to his satisfaction, that Form 1 had indeed appeared in the midst of his plus and minus circles, Chambers reported his result to me, because he knew that I believed in the non-helicity of DNA. Clearly, I thought, and said, this proved that DNA was, in fact, not helical, which I'd been saying for years. The obvious explanation for the appearance of Form 1 was the scenario portrayed on the top line of this slide. But, to my astonishment, Chambers still didn't agree. In fact, although this was, in my opinion, an observation of surpassing importance, Chambers never even published it. Why not? Because he believed that there was another explanation for the results, as per the bottom row of pictures on this slide. Chambers told me that, according to his formulation, there was a 3-step process. For the first step, one of the strands broke open spontaneously. This, of course, is not only possible, but likely over time. 2, the broken strand wrapped itself around an intact complementary strand. This too is entirely possible, and might even be expected over time, even in the refrigerator. So far, Chambers was proposing nothing unusual, but then he proposed that the nicked strand, once wrapped around its complement, spontaneously sealed itself. This, he explained, was a reaction mediated by an enzyme. What enzyme? Water. What? How can this be? I asked. Chambers took me to a blackboard and drew a detailed reaction mechanism with water as the enzyme. His hypothetical reaction mechanism looked impressive on the blackboard, but off the blackboard, out here in the real world, it was thermodynamically absurd. The fact that DNA spontaneously accumulates nicks on storage is painfully well known to every nucleic acid scientist. How can a population of chromosomes, which spontaneously accumulates nicks, simultaneously accumulate a resealing of those same nicks? It's impossible. Every graduate student and postdoc has, at some point, awoken in the morning to find his painstakingly prepared Form 1 had degraded into Form 2, as depicted on the top of this slide. But what graduate student in the history of science has ever awoken to find his sloppily prepared Form 2 had magically resealed itself into pristine Form 1? It's never happened. Now here's the kicker. By a stretch of the imagination, it could be proposed that nicked and resealed DNA were energetically equivalent, so that water really could catalyze the resealing of nicked strands. It's true, after all, that topoisomerase requires no energy source. Even this notwithstanding, however, what would cause the DNA in the Chambers experiment to become 5 to 7% underwound before sealing to produce a single topoisomer containing the native supertwist? It's absolutely impossible. And without the exactly correct amount of underwinding, there's no way the product could ever have been identified by either ultracentrifugation or electrophoresis. At some level, Chambers understands the importance of what he has observed. In accordance with this, he has in the past given me permission to describe his work in my publications, even though he still cannot accept the most obvious conclusion. I last spoke to him about a year ago. He's long retired, and he no longer has his laboratory notes from this period, but he stands by his observations to this day. Since the work is unpublished, you are free to doubt or disbelieve. But the Wu study, to be described next, is published and difficult to controvert. About the best you can do is just ignore it. That, in my opinion, would be tantamount to standing on scientific thin ice. Tai-Tai Wu, whom I believe has elucidated the most probable structure for DNA in living systems, went to medical school in Hong Kong, then got his PhD from Harvard. He did DNA research at Cornell Medical College for some years, but made himself so unpopular because of his unorthodox opinions about DNA structure that he felt ostracized. He now practices immunology at Northwestern and seldom makes public statements about DNA. I'm going to read through this now, even though it's hard to comprehend without pictures. I'll show you some of the pictures shortly, but most of them are provided in part 2 of this series, entitled The Probable Structure of the Protamine DNA Complex, which fully develops the structure we shall now briefly describe. The article is called Secondary Structures of DNA, and it's from PNAS. In this paper, Tai-Tai Wu discussed the pitch-to-diameter ratio for the Watson-Crick double helix at 66% and 92% humidity, as revealed by X-ray crystallography. He proposed that the diffraction pattern of DNA at high humidity was less suggestive of a single Watson-Crick duplex than it was of a pair of identical duplexes, each one stretched out to twice the normal length, with their base pairs mutually intercalated. In other words, as I shall illustrate in a moment, he was proposing that at high humidity, DNA crystallized as a four-stranded structure consisting of two intertwined Watson-Crick type duplexes. It is evident from the publication of the paper in PNAS in the first place, and secondly from the lack of any serious criticism subsequent to its publication, that the idea was considered to be an entirely reasonable interpretation of the X-ray data, although not necessarily the interpretation of choice for DNA in the real world, where genetic considerations seemed to greatly favor a two-stranded model. There is no doubt, however, that even at that early time, Wu was in fact thinking of DNA in the real world. In his own words, at 92%, the surrounding of the DNA fiber resembles that inside a cell, while at 66%, the state of the fiber becomes completely artificial. The differences should then provide the necessary clue for us to resolve the intricate secondary structure of DNA in vivo. After a thorough analysis of the X-ray diffraction patterns of DNA at the two humidities, Wu concluded that, quote, if the structure of the DNA fiber at 66% consists of a double helix, then at 92% it must consist of two double helices. In the Wu structure, the distance between base pairs in either double helix was twice as large, that is, 6.8 angstroms, as in the Watson-Crick structure. But in the end, the stacking of bases at the more familiar 3.4 angstrom spacing was preserved by mutual intercalation of the base pairs of the two adjacent duplexes. Finally, and most surprisingly, he predicted that at 100% humidity, that is, the condition prevailing in living cells, the two mutually intercalated duplexes would lose all vestiges of helical twist and exist as a pair of what he referred to as straight ladders, having their base pairs mutually intercalated. Wu's paper in 1969 attracted little attention and caused no great uproar. But in the years that followed, he began to understand that superhelical DNA, as illustrated in the slide, provided the basis for the four-stranded structure he had proposed. He came to the conclusion that viral and plasmid DNA did indeed consist of two mutually intercalated double helices, each one stretched out so that the base pair spacing was twice normal, but with mutual intercalation of base pairs restoring the familiar 3.4 angstrom spacing between adjacent base pairs in the four-stranded structure. Since this subject is covered in detail in the second presentation in this series, I will show the pictures, but without much comment. This is Wu's own highly schematic diagram of his proposed structure for circular chromosomes. I found it confusing when I first looked at it, so I'll try to walk you through it quickly. The single-stranded circular anti-parallel sugar phosphate backbones for the entire chromosome are represented by the elongated circles on the sides. I should note that although Wu presumes a superhelical twist will be found in purified protein-free circular DNA in the laboratory, he makes no attempt to portray that superhelical twist here, depicting only what he refers to as the straight ladder aspect of the four-stranded structure. The rectangular shapes attached to the backbones are not individual bases but base pairs, the small number shown obviously representing a much larger number than can be drawn in a picture like this. In order to clarify the drawing, the base pairs in the back have been arbitrarily shaded, and the base pairs in the front have been left white. This hopefully makes the mutual intercalation of base pairs easier to see. The longitudinal backbone distance between adjacent base pairs is 6.8 angstroms, which, after the intercalation, gives the more familiar 3.4 angstrom spacing expected for DNA. Thanks to the generosity of Mercury Computer Systems, I have been able to create a true and detailed virtual model of this structure. This is what it looks like. It's merely untwisted, stretched out Watson-Crick DNA. Without the helical twist, the base spacing becomes the same as the residue spacing in the sugar phosphate backbone, which is always in the neighborhood of 7 angstroms. Again, let me remind you that this structure will be described in much more detail in part 2 of this series. Here's a movie of the structure. This is the second duplex, which will intercalate into the first. And here's the final structure. When animated, it's really quite lovely to look at. It's simple, logical, and even aesthetically pleasing. Hopefully your eye perceives the direction of spin as being to the right, because if your eye is playing that perspective trick on you and telling you that the structure is spinning to the left, then it will not seem simple and logical, but complex and confusing. Unlike the other proponents of non-Watson-Crick DNA structures, Wu did not stop with a theoretical paper. He went on to design an ingenious experiment to prove that his structure was real and widespread in nature. Here is the experimental design in his own words. Since the complementary DNA strands of most plasmid molecules are of about equal molecular weight and their charges are the same, it will be very difficult to separate them on agarose gel electrophoresis. However, one strand of the plasmid DNA is the sense strand and one the antisense strand. While RNA transcription is occurring, D loops are formed with mRNA paired with one strand of DNA. Since under agarose gel electrophoresis conditions, RNA-DNA bonds are tighter than DNA-DNA bonds, with a reference given, these RNA-DNA bonds will be maintained and promote the separation on the gel of the weaker DNA-DNA structure. The principle, which is really quite ingenious, is illustrated in this drawing, depicting two D loops. The DNA is black, and the freshly synthesized mRNA in the D loop is red. The DNA, for the purposes of this illustration, is somewhat arbitrarily represented as having a gently undulating, rodly side-by-side structure with no full helical twists. The D loops are, of course, greatly exaggerated in size here, but the principle is well represented by the drawing, which shows that transcription only takes place on one of the two strands, namely the sense strand. Because the RNA in the D loops is linear, having none of the topological constraints imposed by circularity, it will effortlessly wrap itself around its DNA template, whereby the resulting RNA-DNA hybrid duplex will assume the all right-handed Watson-Crick structure, since there's nothing to prevent it from doing so. Since these hybrid duplexes have the most stable known conformation, namely the Watson-Crick right-handed double helix, it is not surprising that they do not dissociate during electrophoresis. Note, however, that the main body of the chromosome remains in the TN conformation, which, topologically speaking at least, is 50% left-handed. In the absence of the nuclear proteins necessary to support this structure, it has a relative instability compared to the more stable right-handed Watson-Crick structure in the D loops. In the presence of substantial amounts of bound mRNA, the sense strand no longer has the same structure as the antisense strand, the latter having no bound RNA. Therefore, as electrophoresis progresses, the two strands, which now have different densities and structures, will slowly separate, as hopefully suggested by the large arrow. In order to ensure a clear-cut result, Wu grew his cells for 3 days to stationary phase, so there would be no replicative intermediates to confuse the results. He also set the electrophoresis current to the low setting of 10 milliamps, so that the electrophoresis could be continued for 48 hours. This is figure 7 from Wu's paper. It looks like a single large agarose slab, but if you look at the time notations at the top, you'll see that this is actually a composite of 4 gels. In order to get through this before we all die of old age, let's use the magic of computer graphics to separate the gels so we can see exactly what was happening at each time. These are the gels, separated for easy comprehension and excluding the 48-hour gel, since all relevant changes had taken place already by 36 hours of time. In each experiment there are 3 lanes. The right-hand lane in each case contains the Form 1 experimental DNA. This is the plasmid DNA grown to stationary phase so that there are no replicative intermediates, but, presumably, lots of mRNA-containing D-loop structures. The middle lanes contain the control experiment. This is the same DNA, but intentionally cleaved with the restriction endonuclease PST1, obtained from New England biolabs. These chromosomes are thus linearized and no longer have any of the peculiar topological properties of circular DNA. The purpose of this control is to answer to any critics who may wish to suggest that Wu's circular DNA was accidentally nicked. The control DNA is intentionally nicked, and any behavior of DNA in these experiments, which is the result of strand cleavage, should therefore be seen in both the experimental and control lanes. The left-hand lanes contain 6.0, 3.6, and 2.4 kilobyte molecular markers. Well, here are the results. At 12 hours, the intact Form 1 plasmid band is beginning to show signs of splitting into 2 bands. At 24 hours, the split is definite, and at 36 hours, the bands have separated entirely and begun to diffuse. This diffusion is characteristic of single-stranded circular DNA molecules, such as Phi-X174 single-stranded virion DNA. The staunch Watson-Crick helicist will surely try to attribute the separation of these strands, widely believed to be hopelessly topologically linked, to accidental strand breakage. Unfortunately for them, that explanation will not work here. Look at the middle lanes containing the intentionally linearized control chromosomes. They remain as single, sharp bands even after 36 hours. The really astute observer, cognizant that D loops are surely also present in the linearized control chromosomes, may ask at this point, if D loops change the relative electrophoretic mobility of the 2 strands of the chromosome, why don't the linearized chromosomes also undergo strand separation in these gels? This is an excellent question, one which Wu does not go to any great lengths to answer. I would propose that the correct explanation is the same one I gave a moment ago, namely that the TN structure is, topologically speaking, 50% left-handed, and is therefore inherently unstable relative to the linearized control chromosome. The latter, once nicked, is free to assume the all right-handed Watson-Crick structure. This is the most stable known structure for duplex DNA, and evidently does not undergo strand dissociation in these gels. At grave risk of being accused of demagoguery, I have prepared a semi-animated version of the Wu experiment, which dramatizes the splitting of the circular DNA sample into 2 bands. I think this little bit of cinematic melodrama is justified, because mere print publication of this remarkable discovery in the year 1999 had no impact on science whatsoever. Therefore, the discovery needs to be publicized. Some skeptics might be prepared to accept the splitting of the DNA into 2 bands, but might still demand to know, with more certainty, what those 2 bands actually consisted of. Wu addressed that question in a very direct and compelling way. His experimental plasmid chromosome from the plasmid PHTB4 contained the sequence shown in the slide. 2 probes, and I won't bother to read out the sequences, but they are identical to the chromosomal sequences matching their colors. 2 probes were synthesized by the Northwestern University Biotechnology faculty. On southern blotting, the former probe hybridized to the faster-moving band, whereas the latter hybridized to the slower-moving band. Wu did not stop there. Next, he repeated the entire experiment with a second plasmid called PUC19, with the same result, that is, 2 bands on electrophoresis. He then cut out the bands, purified their DNA, and used them as templates in DNA sequencing. This time, instead of asking his colleagues at Northwestern to synthesize primers for him, he used commercially available primers specific for the PUC19 plasmid. The result was that each primer initiated DNA synthesis efficiently on DNA from only one of the 2 bands. For those of you not familiar with DNA sequencing, the object of doing it in this particular case is not to determine the actual DNA sequence, but merely to determine whether or not the primer recognizes and binds to the DNA. If so, sequencing will proceed. If not, there will be no sequencing. And if the DNA in the band is mixed, then the result will reflect that. Here are the details of the DNA sequencing experiments. Plasmid PUC19 was purchased from New England Biolabs. Wu also purchased 2 primers for PUC19 DNA sequencing. I won't read the sequences, but here they are. These were also purchased from New England Biolabs. DNA molecules from the slower and faster bands, respectively, were then sequenced using these 2 primers separately with sequenase, purchased from United States Biochemicals. Here are the results. For those of you who are not familiar with the details of DNA sequencing methodology, I won't waste time describing the technique. The important point here is not the sequence itself, but the recognition of the template DNA by the primer. Please note that we're not looking at the dots in this figure, but rather the horizontal bands which appear in the various lanes, giving them an appearance reminiscent of metaphase chromosomes in replicating eukaryotic cells. If the bands are dark, then DNA sequencing occurred, demonstrating that the primer recognized the DNA. If the bands are light or non-existent, however, then DNA synthesis was reduced or absent, demonstrating that the primer did not find its complementary sequence. This is how Wu described the result from Figure 8 of his paper. For each primer, the 4 lanes are A, C, G, and T. For the slower band, primer number 1233, shown in the left 4 lanes in Figure 8a, gave much more intense signal than primer number 1224, shown in the right 4 lanes. Again, remember, we're looking at the darkness of the horizontal bands, not the dots adjacent to each lane. On the other hand, for the faster band, the reverse was true, as shown in Figure 8b. Thus, the slower band consisted mostly of one strand, while the faster band consisted mostly of the complementary strand. Some cross-contamination could not be avoided since the 2 bands were very close on the agarose gel. Well, this concludes part 1 of our slide presentation on the history and science of topologically non-linked DNA. The purpose of this portion of the presentation is not to persuade you to adopt my ideas about DNA structure, but rather to get you to think. What is the structure of DNA? Have we thought the problem through, or are we just blindly assuming that the Watson-Crick structure, first discovered in synthetic laboratory crystals, must be the structure of DNA everywhere else it's found? I've showed you that the so-called mountain of evidence in support of the Watson-Crick structure is, in fact, a molehill, and that, moreover, it's a molehill of false logic. The logic, as we have seen, goes something like this. DNA must have the Watson-Crick helical structure because no other structure is possible. Circular DNA must also have the Watson-Crick structure. Since it's invariably superhelical, it must also be underwound. Therefore, any DNA which is found to be superhelical must have the underwound Watson-Crick structure. Sounds childish, doesn't it? And yet this is precisely the logic which has prevailed in this field. What do you think? Do you really believe that all superhelical chromosomes must have the underwound Watson-Crick structure? What about DNA replication? Do you really believe that all, or even part of the chromosome is constantly spinning at 20,000 RPM? Or not? Never mind what I think. What do you think? Does DNA replication proceed like this? Or this? What strikes you as more plausible? And why should small circular chromosomes always be superhelical? Is it because they are mysteriously underwound, so that they need to be nailed to the surface to stop them from twisting? Isn't that an awkward presumption? Or could it simply be that the superhelical twist arises logically and naturally as a result of the nature of the structure, being topologically 50% left-handed and 50% right-handed, and having been taken out of its normal environment where nuclear proteins support its non-twisted structure? What do you think? You may object to my speculations about the failure of the strands of circular DNA to separate at high pH, making reference, as they do, to a hypothetical form 4 structure whose phosphate groups are in the middle. But at least my structure was proposed by the world's greatest expert on the chemical bond. The establishment dismisses all this, alleging that form 4 is just a tangled mess with no structure at all. It doesn't matter what I think or what they think. What do you think? Then I've shown you the evidence. Crick's paper starts by assuming that DNA is a double helix, then concludes at the end that DNA is a double helix. Do you accept this as a logical argument? Weissman's paper describes an attempt to reanneal DNA at what appear to be arbitrarily and capriciously chosen conditions of pH and temperature, and claims to have created tNDNA, reporting that it is not normal. The experiment is essentially uncontrolled, since the purported control experiment uses a different DNA in a different solvent at a different pH, temperature, and time of incubation. What's missing in this picture? Do you believe that this experiment really proves anything at all? Bob Chambers refused to publish his discovery. Single-stranded complementary circular DNA spontaneously reannealed back to a form having the properties of native form 1 in his refrigerator over a 3-month period. I say the top mechanism is the only way to explain it. Chambers says it's the bottom mechanism, even though it's thermodynamically absurd. What do you think? Is Chambers' mechanism correct or not? Did he merely make a mistake? And should the data just be ignored? You must decide for yourself. Finally, I showed you the work of Tai-Te Wu, who demonstrated, in an experiment which was rigorously and doubly controlled, that the form 1 band can be split into 2 bands by electrophoresis under the right circumstances, and that the 2 bands correspond respectively to the 2 fully intact circular single strands that together comprised the original chromosome. Do you believe it or not? Are you able to just ignore it, regardless of whether true or false? I can't decide for you. You must decide for yourself. If you wish to see a detailed virtual model of the probable structure of DNA in at least one biological setting, with almost certain implications for DNA structure in many other settings, please see Part 2 of this series, entitled The Probable Structure of the Protamine DNA Complex. Thank you for watching and listening, and above all for being willing to think. When there is no promise of immediate financial reward, or of academic positions and honors, it can be very difficult.